So hello everybody, good morning. Welcome to this second day of this optimal transport and application workshop in Pisa. So we have the pleasure to start the morning with a talk by Gabriel Perret from CNRS and the École Normale Supérieure in Paris. We speak about transformers. Transformers are universal in context learners. Thanks, Gabriel.
Okay, thanks, Filippo. It's okay? Okay, so thanks a lot for inviting me. It's always a great pleasure to be here every time to learn a lot of things. And hopefully you will learn some new things from this talk. So this is joint work with two groups of people. So Takashi and Martin on the first part, actually the last part, with the last contribution that I will describe on universality, and Valérie and Pierre on connection between these transformers and partial differential equation. And I would say the goal is more than this contribution to try to convey to you, mathematician, I would say, some mathematical questions that arise when studying these new type of neural networks that are used initially mostly in large language model, but I think nowadays it's really used everywhere. So almost all large neural networks that you would see working well in practice are actually transformers. So not only for text, but also for vision and more and more for many tasks. And I think this is really a total change. The architecture are very different. So I think it's really nice because it's also asking a new type of question that I like, because it's also at the interface with optimal transport. I mean, some questions are related to optimal transport, which is the reason why I present this today. Okay, so what are transformers in a nutshell? So I'm going to make I would say, high-level description, and then I will write down a more mathematical equation to explain exactly the type of model we are considering. But I think the big paradigm shift, is the fact that each data is not going to be a vector, but a point cloud. Okay, this is the main take-home message of this talk. When you want to study transformers, you don't want to study functions that operate on vector, but you want to study functions that operate on an infinite dimensional space, which is a space of basically point cloud, and of course, because we are here in Pisa, on the space of probability distribution. And I think it's very exciting because it's open a lot of questions. Okay, why is so? So I'm going to take the example of text, but it's something you can apply to basically any type of data as soon as you have a way to break it into small pieces. So for text, what you do, it's called tokenization. You take your text and you chunk it into small groups of letters. Could be word, or most often it's a few group of letters. And then each of these group is going to be replaced by a vector. And then you put all these vectors together, and this gives you a big point cloud. So each of these vectors represent one of the tokens. Okay, and also what you do on top of this is, of course, because this would break the ordering of the sentence, what you add on top of this is a vector that encodes the position, okay, and you sum it, which means that the information that is contained in each of these vectors encode both the semantic, what the letter mean, and also the position in the sentence. But more or less after this, so you can treat this as a pre-processing, the neural network, the architecture, is just going to be a function that transforms a point cloud to another point cloud. Okay, so really the core of the type of question I would be trying to ask is understanding what is the geometry or what is the class of function mapping groups of points to group of points, or more generally, probability distribution to probability distribution. For instance, a partial differential equation, an advection equation, could be an example of an operator that maps a group of points to a group of points. Okay, and transformers are really in this spirit. Okay, and this is for text, but you can do this for images. For instance, you would take your images, chunk it into small patches, and each patch would be a token. Okay, if you think about a protein or a graph, you would take your big graph, chunk it into small subgraph, and then represent your small graph using vector, and then your graph would be encoded as a group of points. Okay, so it's really a philosophy that you can apply everywhere. And if you have a multimodal data, like text, video, audio, and whatever, you just chunk each part, and then you make just a big soup out of everything. So it's really something that is both very simple and very convenient. It's a unifying way to represent a very complex data. Okay, so now, of course, the big question is what is going to be this architecture? This architecture are actually very simple because they just repeat a lot of times the same operation. Okay, and the main building block of this operation is what is called the attention mechanism, and it's going to be the focus of today's talks. We are really going to speak mostly on this part, which is the part where the tokens are going to be mixed together. exactly like in particle system, and I guess Cathy would probably speak about this, is exactly the same idea. You have particles, they would speak together and they would move to another location. So obviously it's the most important or exciting ingredient, it's attention. Attention were created a bit before transformers. Okay, so the transformers paper that was 7 years ago now is basically the idea that you take something that was already known in natural language processing and you're just going to repeat it over and over. And the name of the paper is Attention is All You Need, because they show that just using attention is enough to make the best, basically, neural network ever created. But you have to remember there is two little additional ingredients that I'm going to describe. But basically, these are going to be the three ingredients. Okay, I'm going to go over. So what you do, you take your point cloud. Okay, then you apply this ingredient several times. Each time you apply it, it's a layer. You apply it n time. And basically, the difference you see in the different neural network that you can use is just the number. I mean, there is two parameters you can play with. Is the number of layer. If you increase the number of layer, you have a bigger network, and also the dimension of the point cloud. Okay, so if you want a bigger network, you just increase the dimension of the embedding, and you increase the number of layers, and you have a more powerful network, which can go to billions of parameters. So the very large language models, they have hundreds of billions of parameters. Okay, so you repeat this over and over. Your point cloud is going to move to another location. Okay, and then depending on the task you want to achieve, you put a final layer that gives your decision. In natural language processing, usually what people want to do is to create text. So if you use a large language model, usually type a prompt, and then the network is going to create new token over and over. So what you usually do is you take the last point in your point cloud, the one that represents the last word, and then you map it using a small neural network to a probability over the language, over the set of tokens. Okay, and then you predict your next token, for instance, by the point that has the highest probability. Or if you want to use randomness to generate a random text, you can draw at random a token, a next token from this probability distribution. So this is for natural language processing. For vision task, usually what the transformers are used to is to denoise images or to improve the quality of images because maybe you want to increase the quality, or in fact because you do what is called a diffusion model, you are going to create random images by diffusion. So you just simply here, instead of predicting probability, you predict new images. Okay, so depending on the task you want to do, you might want to change this, and I'm not going to really speak about it. Okay, so what are these maybe these three operations? The first one is very simple. It's just a projection on a sphere. You're going to take each token independently and project it on a sphere or on an ellipsoid. It's actually very important because you would see the attention operator is very ill-posed, very sensitive. So you really want to be very careful about the norm of the token. Okay, but this is very easy. Then there is the attention I'm going to discuss. And the last point is a small neural network that takes independently each token and map it to a new location. Okay, so what is important is the attention are going to be the only operation that mix together the token. This one and this one, mathematically, they are just going to be a fixed push forward, if you want, that takes your group of points and just map it to another location. So somehow they are quite easy. What is the attention mechanism? The attention mechanism is exactly like a particle system in interaction. You're going to declare that the new position of the token is just going to be a weighted average of the previous one. Okay? So this is going to be just a weight matrix, call it, I don't know, Wij, and you're just going to be doing a weighted sum of j, of Wij time the previous location. So it's like a barycenter, but of course it's a nonlinear averaging, just as when you do a PDE with interacting particle system. And this is the equation for the weight. Okay, so the weight are morally the exponential of the inner product between the pairs of vector. Okay, you simply, and this is very important, and I think this would be a key distinction with many PDEs that probably you study, is you do barycentric sum, so you normalize so that the sums to 1. Okay, so you would have this division which would create some extra nonlinearity and also some difficulty because, of course, if this is close to 0, you're going to divide by 0, and this might be a bit ill-posed. This operation, maybe, I don't know if you're familiar with it, but it's very popular in machine learning. It's called the soft maxed operation. You take the exponential and then you divide by the sum. It's a way to approximate the maximum operator. But anyway, it's just the formula. And the only thing that you would play on, and it's very important, is the way you compute the inner product. So this kernel, if you want, is going to be parameterized by the metric you use to compare the token. Okay? And the metric is parameterized by two matrices, Q and K. So they might reduce typically the dimension. So the inner product will typically be computed in a lower dimensional space. And this is the two buttons you can play on, the Q and the K. So Q is for query, K is for key. This is the naming in natural language processing. These are the two matrices you are going to play on, and usually put an extra matrix to, for instance, be able to rotate the space. But this extra matrix, you could factorize it into the MLP, but it's usually convenient to write it like this. Okay, so for each of these attention layer, you have three matrices, Q, K, V. And of course, since you are going to repeat it a lot over and over, you have a lot of collection of matrices, and this makes a lot of weight. Okay, but you have to remember that also the MLP has some parameter. So in big language model, most of the, you also have a lot of parameters that are put inside the MLP. I'm not going to discuss this in details, but roughly speaking, you have as many parameters in attention and in MLP, and this makes a lot of parameters. And that's it. It might look a bit complicated, but it is way, way more simple than any other neural network you might think about. It's basically just repeating this operation hundreds of times. So I think it's good to know that actually big neural networks, they are, in spirit, quite simple to describe. So what are the questions that I think are new and interesting? I think the most interesting question is the fact that this operator, they can operate in infinite dimension. They can deal with arbitrary number of tokens. Okay, this sum, of course, you can replace it by an integral, which I'm going to do. And at least morally, you can apply it to an arbitrary number of tokens, which means you have to make a mathematical analysis in infinite dimension because they operate over a priori an infinite dimensional space. And if you state a theorem, you want to know exactly if the constant depends on the number of tokens, and ideally, you would like a theorem that doesn't depend on the number of tokens. Of course, you have to deal with a possibly very large number of layers, but now this is quite, I would say, customary in machine learning to study neural network with possibly an infinite number of layers. And I think it's no secret that what you would have to do is instead of considering a discrete recursion, you would consider a differential equation or a PDE. And this is rather well understood. And the type of question would typically to understand what this neural, the two types of question I would say would be understand what this type of architecture can do, what type of functions they can represent. So it's what would be called expressivity, universality, interpolation properties. And the other question that I will mostly not address because it's very hard is to understand what happens when you train the parameter. Because of course the goal, during training is to learn the Q, the K, and the V's to achieve the best possible performance. And can you do it? Can you do it by gradient descent? I would say it's mostly an open question. I will briefly mention it, but I would focus at a very simple question, which is, can you represent any mapping? And can you say something about this type of operator? Okay, so first, what I would do is I would just rewrite all the equations, sorry about this, but with, I would say, a clean notation to be able to lift it over the space of measure so that we'll all agree on the type of question we want to study. And this brings this idea of what people in machine learning call the in-context mapping, which for us is very natural. I think everybody does this all the day in mathematics, but I would say in machine learning, they somehow like to emphasize this, is that the vector field you would be dealing with is not autonomous. It depends on the measure itself. It depends on the distribution of points, which in natural language processing, they call the context or the prompt. It's basically the set of words that are before you. Okay, or in an image, it's a set of patches that are around you. So when I would write a mapping, so typically gamma would be the letter I use for the vector field. Of course, the vector field depends on your position, but it also depends on the set of points that are around you. Okay, so it might be a bit heavy notation, but I'd like to stress that the mapping, they depend on two variables, little x, the space variable, and capital X, the group of points. And it is basically exactly the same equation as before, just to emphasize that it depends on the set of tokens. So it's really like an interacting particle system. If you don't have the division, it's typically what you would have if you study a group of points that interact together through an exponential kernel. Just to mention that there is in practice, what people would do is at each layer, they would not consider just a single attention. Just as in neural network, usually you don't have a single neuron, you have a lot of neurons that operate in parallel. So in a large language model, what they would have is they would typically have, a few dozens, I would say, of attention that operates in parallel. and the output would just be the sums. Okay, so instead of having just a single vector field, what you would have is just a sum of these vector fields at each step. It really just doesn't change much into the equation. It's just to mention that in practice, you have a parameter capital H, an extra parameter, which is the number of head. So usually it's like 16 or 32. I mean, depend on the choice. And the design practice, what has been found to be working the best, is that if you increase the number of heads, okay, what you do is you decrease the dimension over which you compute the inner product. It's totally heuristical. There is, I mean, a priori no mathematical reason for doing this. But I think it's important because it says that even if you increase the number of, let's say, neurons or heads, you don't change the total number of parameters. Okay, so basically, at each layer, what you have is 3 matrices of size d times d. So the number of parameters in each attention layer is 3 times d squared, whatever the number of heads. And this is, I mean, the design practice. So what I've said is if you want to increase the number of parameters, you can play on the number of layer and on the dimension. And experimentally, they have computed what they call scaling law, which is like a curve that tells you that if you want to increase your neural network, by how much you should change the number of layer, and by how much you should increase the dimension. And this is totally empirical. So people have devised empirical scaling laws of language. And there is like very influential papers about this. So this is about the most important part, the attention. But don't forget that you have 2 other set of maps that are called context-free because they are just push forward. They don't depend on the context. The first one is just a very simple neural network. So in the most simple neural network are 2-layer neural network, which is just you apply a matrix, then you apply the ReLU, which is just a very simple non-linearity, and then another matrix. Okay. So here you have 2 matrices, and I think the design is that the dimension in between is 4 times the dimension. So the number of parameters in this is 8 times d squared. You have 2 matrices here with the number of parameters is 4 times d squared, and that's the way it is. So it's like the dogma, it has been studied that the factor 4 is the best. But I will not speak about this a lot. It's just if you want a fixed, I mean, it's just a push forward, the points they don't speak together. And the last ingredient, which turned out to be super, super important, most notably because you have this division that is very sensitive to the amplitude of the point, is just a normalization. It's basically a projection on an ellipse. So here you have less parameter. You have basically order d parameter. It's just the size of the ellipse on each dimension and the centroid. And this is also very important. If you remove any of these ingredients, it doesn't work. So there's been a lot of work to freeze, I would say, an optimal, in some sense, choice. And this was created 7 years ago, which looks, of course, very young with respect to mathematics. But with respect to machine learning, the fact that you have an architecture where thousands of people and, I mean, a lot of money, obviously, is putting into trying to do better than this. The fact that in 7 years, nothing has almost changed. This is almost like the same it was 7 years ago. Means that there is some hidden structure, some hidden property of this that are not just by chance. They are things that I think are interesting to understand. Okay, so what I've said is basically a transformer is just a composition of typically hundreds of these three type of layer. Okay, so obviously the goal of the talk is to go a bit beyond this and study what happened. Maybe you can call this a mean field regime or mean field limit, but it's just the fact that you replace sum by integral. There are no mathematics, no mean field. So this is just the same equation, but you replace sum by integral, and then you can at least formally speak about what happened with the infinite number of tokens. And I will give example after. Of course, in practice, you never have an infinite number of tokens. I mean, up to my knowledge, people have never tried to go beyond just like discrete sums, but there's no limitation. The transformers can operate over arbitrary number of points. And then you just have the usual, I would say, traduction from a set of points to probability distribution. Instead of deforming the space, you're going to push forward the densities or the distribution. And what you do when you do a layer is you take your point cloud, okay, at the discrete level, you compute your attention or your whatever layer. So gamma of x would be the context dependent mapping, and then you apply it to itself. But at the level of measure, what you do, which everybody, I mean, probably do on a maybe not daily basis, but very often, is just you compute a vector field that depend on your measure, and then you push forward the measure itself. So the type of formula that you apply with transformers is gamma of mu push forward mu. And this is the type of mapping you want to consider and to study. And just to mention that then what you would do, at least at the discrete time level, if you have a discrete number of layers, is you would just compose this mapping. But of course, this is composition of mappings that depend on the context. So if you compose two mappings, like this to one, the first is going to be conditioned on the input context. But of course, the second one is going to be conditioned on the context modified by the first mapping. So I don't know, maybe someone knows the name of this operator. I call it diamond, but just to mean that this is like a twisted composition rule. And at the level of measure, it's the same. You compute the mapping, but the second measure is the input measure deformed or pushed forward by the first mapping. And I call this the diamond rule. So studying expressivity, universality, whatever, is about understanding what happened when you compose with the diamond rules a lot of in-context mapping, which has some specific structure like this one. This is just a slide to recall for those that are in machine learning, or to teach to people that are not in natural language processing, is that when you do text specifically, this is not for images, just for text, there is an extra level of difficulty, because basically text is causal. So, I mean, it makes sense to preserve the causality structure, to break the permutation and variance. I would say there's two reasons for it. I think they are written here. The two reasons for why you want to make your mapping causal, so to break the permutation and variance. The first one is when you do training I mean, one of the key revolutions of the last 10 years is people have realized that the best way to train a neural network is to just teach on next token prediction. So the task you want to do is very simple. You have a set of tokens, you input xi, and you want to predict xi plus 1 in your data, because in your data you already know the future. It looks very dumb, but nobody has found something clever. Okay, and of course, if you know the future, this is totally dumb, because if you already know xi plus 1 here in your context, predicting xi plus 1 is just about shifting. So this loss will not train anything. So of course, you have to block yourself from the future, which means that you have to restrict the sums to the past. So this is called mask attention. You just multiply your weight matrix so that it becomes triangular, upper triangular. So this is, I would say, one important reason at training. At inference time, when you use the model, the way people use a large language model is usually in a generative way to generate things. They ask a question in the prompt, and then the transformer is going to predict the future. And here, once again, of course, when you use it in practice, you don't know the future, because this is what you are going to use. So in practice, the way you use this architecture at test time is a bit different from train time. So usually this is called teacher forcing. You have a teacher and you force it to predict. And at output time, you do it in an autoregressive way. You have a set of tokens, the prompt. Then you predict the one just after. And then you just iterate this map over and over to stack token one by one. So of course, here you don't know the future, so you have to use similar things. And of course, the difficulty, since now you break the permutation and variance, it doesn't automatically lift over the space of measure. So either you just say, okay, let's forget about measure and we can directly study this, which makes sense. Or if you want to restrict causality, what you have to encode is basically the time or the causal axis as an extra dimension. Okay, so you need to lift your measure. Instead of saying that it's a measure in dimension d, you have to say it's a measure in dimension d plus 1. You have to add back the time variable. And of course, then you can, it's a bit like cheating, but it's a way to reintroduce causality by considering the measure as a graph, living on the graph. And you can also, I mean, say that for each time, so in practice, for each time position, there is a single token in language. But with this, you can consider a space-time measure if you like. You could have even several tokens per time position, which is not what happened in practice, but you could do it. And of course, now if you use this space-time lifting, you can reintroduce an integral, but this time in dimension d plus 1. And the difficulty is that the kernel becomes singular because you have this masking. So typically, this leads to extra difficulties in the mathematics. I will not go into the details. This complexifies a bit the proof, but morally, all the theorems, they stay the same in dimension d plus 1. I just wanted to say this because, of course, in practice, it's very important. Okay, so now what are the two questions we want to ask? The first one is a bit like connecting this to PDE. And in fact, obviously, the first step is at some point you are going to use some Cauchy-Lipschitz argument or to assume that the mapping is smooth. So the basic question we ask, which is also, I think, relevant for application, is are actually this architecture stable in some sense? For instance, are they Lipschitz? So spoiler, they are Lipschitz, but unfortunately, the Lipschitz constant is very poor. So it's explained why transformers, they are like very hard to, I mean, they can be very sensitive to manipulate. So this is, I would say, mostly a negative result, but it's quite interesting. Of course, I would skip the slide on optimal transport. Okay, sorry, I should have done this before. Anyway, so yeah, so spoiler also, the topology is going to be the topology we love and cherish. But obviously, with a natural candidate for this. So everything would be quantified according to Wasserstein, and when you would study PDEs, you would work over the Wasserstein space. So the question is, what is the regularity of this type of mapping? And really here is just first order regularity. But what is important is to try to really assess precisely the value of the Lipschitz constant C as a function of the parameter. So for instance, the QKV matrices. And of course, if you project on an ellipse, I mean, the size of the ellipse will play a big role. It's important in practice to understand a bit the robustness. Can you attack these transformers by changing the distribution of token and so on? And also, when you want to study PDE, you would have to use some Lipschitz argument at some point. The short answer is yes, they are Lipschitz, but you should expect that in the worst case, the Lipschitz constant is going to be very, very large. And what was a bit disappointing is we were not able to have a unifying construction. We have a different Lipschitz behavior depending on whether you have an arbitrary densities or you have a discrete densities. And really the proofs are totally different. In both settings, they are sharp, meaning that you can exhibit measure which reach exactly the Lipschitz constant. But maybe this asks the question to have a bit more unifying studies of this type of mapping, which is my first question to you. And also here, for this, we have to assume a compactly supported. And it's not clear when the measures are not compactly supported, what would be the good hypothesis. I would study the Gaussian case after, in which case it's Lipschitz. But obviously, Gaussian is a very specific case of non-compactly supported measure. Okay, just to tell the result, if you have an arbitrary measure, discrete or whatever, on a compact space of radius r, so think about the ellipse we were dealing with before, the behavior is r square exponential of r square. So it grows really, really fast with r, which is very disappointing and very bad. But at least it's Lipschitz, so if you want to study PDE with compactly supported data, it's going to be okay. Now, what is more interesting is in practice, of course, you have n is large, but it's not infinite. So we wanted to have something, I would say, better. I mean, it's just two different bounds in the discrete case. And in the discrete case, the scaling, which is also sharp, is r square square root of n. So you don't have the exponential of r square. So unless n is like super, super large, this bound is usually much better in practice. But I think this raises the question of bridging the gap between these two proofs. And this proof is really based on a discrete level. It doesn't work with densities. Just a side note, if you want to go to the causal settings, so when you have a time axis, it's going to be non-Lipschitz for the Wasserstein. But it makes sense because in all these transformers, the time variable is stay intact. Okay, if you look at your space-time measure, it's marginal on the time, it's going not to evolve, which is something that happens a lot. I mean, it's quite customary when you have a space-time distribution, which just means that you should not consider a Wasserstein, you consider L2 of Wasserstein. Sometimes it's called conditional Wasserstein, meaning you have to sum the Wasserstein contribution independently for each time, which totally makes sense. I mean, it's just a natural metric. And in this case, it's also Lipschitz. And the constant behave like this one. Okay, just a small remark that you have to change the topology when you deal with this space-time measure. Trying to keep a track of the time. So I think this is the first step toward understanding what happened when you stack a lot of this layer. And I want to insist that here, I'm not speaking about training the transformer. I assume someone give me trained transformers. I'm just trying to understand what's happening, okay, just to be clear. So I assume the key KQV matrices are fixed. They depend on time, but they are fixed. And here, when I say time, sorry, I should not use the word time. I speak about depth. Okay, so you're applying. This is the equation for your vector field, and you're just going to iterate a lot of time, capital T time, this vector field. Each time you create a new layer. So what you would see is that the evolution in depth of your network as a dynamical system, if you want. And since I'm going to take the limit where capital T is very large, the number of layers is very large, of course, you have to renormalize your vector field by 1 over the depth. Okay, and also I forgot to say this, but in all very deep neural network, maybe it's more important than transformers actually, if you want to do very, very deep neural network, you have to do what is called a skip connection or residual network. You have to take the input here and also to add it in front. So instead of iterating gamma, you have to iterate identity plus gamma. It's very dumb, but when people discover this, I don't know when it was, but like almost 10 years ago, it created a revolution because it allows to build very, very deep networks that are very stable. And the intuition, I think, for a mathematician is very clear. If you renormalize, of course, you can absorb this capital T into the V, but I think it's good to make it explicit. You can take the limit of this, and then you get an ordinary differential equation, which is, of course, I mean, under a regularity hypothesis, it's some object that is stable that you can integrate. Whether if you iterate a map a lot of time, unless this map is orthogonal or something nice happen, it's going to diverge to infinity or to goes to zero. So, I mean, this renormalization is obviously the correct one. I guess so. But nobody in machine learning calls this a vector field. So just to, it's my own wording on. So if you read I think reading the transformer paper. Say again? Yes, yes. No, I agree. So maybe I should put X plus from the start. Would be a bit safer because when Filippo is in the room, I have to be prepared. But just I think it's a good thing to do. Open once in your life the transformer paper. First of all, I mean it's a very influential paper. I mean it's well written. It's just not written for mathematicians. So just try to see whether you see the connection between what I've explained to you. So maybe you should thank me because I've tried to understand the paper and write it with equation that I guess I mean we love and it's much better. But it's a very influential paper, just not written with the correct equation. It's written with equation that if you interpret them somehow, you understand. And the paper is like cited 200,000 times or something. So it's really, really influential. But at the end of the day, you really have this equation. I'm not cheating. So in the infinite depth limit, what you obtain is just a set of coupled ODEs, which means that your particle system is going to evolve according to some interaction rule, which is this one. But of course, since everywhere you have permutation invariance, this is really actually a PD. So, and here I use a vector field rightly because you have a conservation equation. It's just translation of this. Instead of particle system, you look at the nonlinear PDs that you have. And it's really a classical type of equation that you have in interacting particle system. I would say the only main difference is this normalization. Because usually, I mean, many cases would disagree with me and have an example of these settings. But in many situations, people study the case where gamma is like a convolution. So this would be a linear function of mu. And here it's like a twisted convolution because you have this normalization, which creates some bit of extra difficulty and some behaviors that are different that I'm going to showcase just after in the Gaussian case. You have a very different behavior, and this normalization play a huge role. So if you remove it, it doesn't work, basically. When I say it doesn't work, it doesn't give good performance. You cannot train and so on. Just to mention that the type of question that would be super interesting to address that I will not be able to do because it's super hard is typically optimal, practical. I don't know the name for this, but practical control. So expressivity is about trying to show the existence of a control, trying to show the existence of parameter theta so that you can drive the red point to the correct blue location. But of course, in practice, you don't really care about just expressivity. You would have to have a practical algorithm to compute this parameter. So you want to have an effective control that is usually obtained by doing a gradient descent on the parameter theta. Okay, so what usually you have an energy, which is typically a next token prediction. You measure the performance of your next token predictor, which is your set of vector fields, and you want to minimize this energy with respect to theta. And the type of question, I mean, the first question is if you do gradient descent, are you going to converge to the global minimizer, which is obviously is non-trivial because it's a very non-convex problem. So there are some analysis. So with my students, this type of question we ask. But obviously, in full generality, having a theorem that works for any initialization is probably not true, or at least very hard. So usually what we do is a local convergence result to the global minimizer. So if you assume that you are not too far from the local minimizer, and if you assume you have enough particles, I mean, there's many hypotheses, you can show typically that you converge to the global minimizer. So you typically have a Poljak-Lojajevic inequality around the minimizer. And I would say it's a very weak form of say that the problem is working well. So understanding this is a typical question that are very important. Yes, but it's a local one, meaning that around the minimizer, you don't have stationary points. Although the function is non-convex, you're going to converge to the solution. With? Well, I could argue that this is an analytic function. So you could argue that you have local PL inequality. but not necessarily with exponent 2. The last function here, so t theta would be the iteration or the PD. So t theta is the operator that would typically map your parameter to this deformation field. OL, it depends on the application. You can think about being just the L2 norm. But for a large language model, usually is, from this, you predict a set of probabilities, so a discrete vector of probability. And instead of using L2, you use the relative entropy. So, but this is just a minor modification. Okay, what I've promised is just a special case to understand a bit better what happened and to see that it's non-trivial, is the space of the set of Gaussians. So if your measure is Gaussian, just a simple computation shows that because of this normalization, actually the vector field is going to be a affine vector field, which means that the space of Gaussian is actually closed under the action of transformer, which I think is very nice. Of course, it's an idealization. In practice, you never have a Gaussian distribution of token. But it means that what you have to consider in this case is just an evolution in finite dimension, so an ODE, over the space of mean and covariance. And this is just the equation for the covariance equation. What is nice is it's closed on the covariance. And it's both simple but non-trivial because the equation is really sigma dot equals sigma square somehow. So first of all, you might expect that for some choice of parameter and some initialization, in finite time, you would have a blow up, which makes sense because here I've totally dropped the projection on ellipsoid. So of course, if you add in this equation projection on ellipse, then I mean you cannot even speak about Gaussians, which is why. But you should, I mean, the typical behavior you could expect is that the ellipse here are going to evolve and become very, very expanded in one direction. Okay, so you might have a growth, and if you really are in setup, you can even have a blow up, so the covariance might become the rank deficient in finite time. But what makes it very non-trivial is these are matrices. And so in 1D it's trivial, of course, you can integrate it explicitly, but in higher dimension, because you have non-commuting matrices, they don't commute and they don't commute with your initialization. It's impossible, even if it's simple, it's not possible to solve it explicitly. So understanding this ODE, although it looks simple, I mean, at least we were not able to understand it. In some special case, like when V is identity, you can show indeed that it would converge to stationary points that would be rank deficient, which is a bit the take-home message of a paper by Cyril Le Truit and collaborators that shows that in the particle system case, under very strong hypothesis, so it doesn't work for any matrices, then the group of points are going to collapse to a single Dirac, okay, which is a non-trivial result. This is really a discrete result, and we could see this as a Gaussian counterpart of the fact that you would have some collapse of the distribution. So I think just understanding this PD a bit better is interesting. The last part is about expressivity. I would be fast on this because the result is quite simple to understand. I'm just going to sketch the proof. Spoiler, is going to be just Weierstrass theorem, so it's kind of just like what we would do to show universality of polynomials. But of course, here the twist is we are doing this in an infinite dimensional space. Okay, so remember what we are considering is basically composition of this type of mapping, composed also with context-free mapping, so just a small neural network here. As for the classical Weierstrass theorem, you have to work on a compact space, so it's not clear how to extend it to non-compact domain. But at least if you are on a compact domain, you can treat your set of context as being itself compact because it's a probability distribution on a compact domain. So the input is a compact domain. Okay, and the theorem says that if you consider an arbitrary in-context map, for instance, some gold standard that would be predicting the next token. So gamma star is the mapping you want to approximate, depend on both the context and the token. There exists capital N, okay, and there exists a choice of QKV matrices so that you approximate it uniformly on your compact. Okay, and I think what is interesting and novel with respect to existing work is that single transformers work for an arbitrary number of tokens, even with an infinite number of tokens. Okay, because of course you could restrict yourself to a fixed number of tokens, then you're back to finite dimension, and then you could use classical. I would say classical. I mean, there is this proof that would show that these architectures are universal, but then the constant and all the parameter will grow if you increase the number of tokens. Here, I mean, it's totally blind to the number of tokens. And also something that is important is all the matrices, they have dimensions that are proportional to D, actually 4D. So we don't cheat by taking V matrices where the dimension will grow with the number of particles. Because of course you could take your set of points, encode it into a single particle, and then consider you have a single particle and crack the problem. And this would be cheating. You don't want the dimension to grow, and also you don't want the number of edge to grow with the number of particles, which is different from what was proved before. I think this was interesting, but this was not really addressing the question that was raised initially. So I think still have 3 minutes maybe. Just to say a few words about the proof. And the proof technique is a bit boring and not very interesting. So I think one question would be to have a better proof with better constants and things that would be a bit more controlled. But the way you do the proof is by basically crafting an algebra, because you would use Weierstrass theorem, and show that this algebra separate points so that you can apply Weierstrass theorem. And the algebra we have been considering with Takashi is very simple. It's just first in 1D, because Weierstrass is in 1D. Just the composition of an attention with the affine transform. So the MLP, the small neural network, is just an affine transform. So that's going to be a function of this form, which a priori is not an algebra. So to obtain an algebra, we simply multiply together a lot of these functions. So it's really the most dumb way to create an algebra is just multiply functions together, and then is define an algebra of functions. The first step, which is very painful, and I'm going to skip, is to show that this type of things, you can actually implement this with transformers, which a priori looks a bit weird, because transformers are composition of function, where this is just a multiplication. But obviously, by just increasing the dimension, you can write a multiplication as a composition over the space of dimension twice. So, I mean, it's kind of a trick, but by increasing slightly the dimension, you can view this not as a multiplication, but as a composition. Also, when you do this diamond composition, you have to advect the context. And here, when I'm doing the multiplication, the context is not advected. Each of these functions, they are applied to the same input. So once again, you need to increase the dimension to emulate advection by just like the same, you're just going to transfer the same identity mapping over and over, which is basically the reason why you have to increase by a factor 4 the dimension, so that you can write this as a composition using this diamond operator that I don't know how you call it. So these are just like minor details, but the take-home message is this type of function, you can implement them using transformers. The second step is to apply Stone-Weierstrass results. So you have these basic monomials, if you want, that you're going to multiply, and you show that they are dense by just showing the hypothesis of Weierstrass, that is compact, that the functions are continuous for the Weeks topology. Actually, we know they are Lipschitz. That you can implement constant function, and that you can separate point, meaning that if you have a context and a token, so that they have equal value for each. You have two mu and you have two contexts, a pair of contexts and a pair of points that assume the same value for each of your monomials. You want to say that they are equal, and this is just easy. I mean, you just check. You just set to 0 this, so that x and x prime are going to be equal. Okay, and then what you have to show is once again you select another set of parameters. Is that this type of integral is injective. So it really looks like a Laplace transform, except with a normalization. But I spare you the details, and you can easily show that this mapping is injective over the space of measure. So it's kind of taking care of this normalization in a neat way. So if you're interested, you can just come to me, and I can explain a bit in detail the proof. But the proof is not very complicated. I want to spend some time on the conclusion, very, very fast, just to insight on some key questions. I think one first thing is about the Lipschitzianity or the PD behavior about these mappings. What we saw first is there was a discrepancy between discrete and mean field, and I think this is not really nice. We would like to understand better. And also what is a bit more worrying is in practice, you don't see the square root behavior. If you take a pre-trained, you download some architecture and you look at what is the local Lipschitz constant, what is actually the constant for each set of tokens, you see a behavior that is more like n to the power 1/4. So we saw a discrepancy that we don't really understand. Also, if you generate random transformers, they are exactly this constant, which means that probably the square root of n is too pessimistic, and maybe there are some hypotheses to put to get a better Lipschitz constant, and we don't know how to do it. To universality, I think one big question is to have something that is more quantitative. So if you assume your function is not only continuous but Lipschitz or even maybe even more regular, Can you quantify a bit more the number of layers you need, the dimension, and so on? So to have more quantitative statement would be super nice. Um, and the last question that I didn't address at all is to understand the training. Both, can you actually train these transformers? Can you show that it's easy to train? And also, can you explain a bit what are optimal transformer architecture? What are they doing? What do they look like? This is also not well understood. I mean, there is many design choices that are totally questionable, and it would be interesting to understand why do you take exponential and not some other function? I mean, okay, thanks a lot for your attention.
So many thanks, Gabriel. Some questions for Gabriel? Please.
Thanks, Gabriel, for very nice mathematization of the transformer paper. So I have a question about one thing you didn't talk about, which is the positional embedding of the tokens. So that's very important in practice, but also gives you a lot of freedom. For example, what do you take for dimension of the space? How do you position the initial tokens, etc.? Do you have some insights on that?
So position encoding is very important, and also one thing that people are now doing for, like, I would say, 2 or 3 years. Here I've cheated a bit. I've said the positional encoding only happened at the beginning, and after nothing happened. But in practice, for large language model, now they do. They change they change the definition of attention so that also at each layer you have. And somehow this is like a bit like if you see the attention matrix as a convolution because you are in 1D, it's a bit like forcing the convolution to decay at infinity, which obviously makes sense because well, if you want to treat a very large number of tokens, you need some decay. So I think indeed, if you don't use the positional encoding, it doesn't work in practice, and also you would like compactness if you have if at the discrete level, if you have an infinite number of tokens, if your kernel doesn't decay, something will be wrong also mathematically. So I mean, it's something to take into account for sure. But I just want to mention that now transformers they actually embed this at each layer, not only.
Thank you, Gabriel. Just a mathematical curiosity. Could be interesting to consider maps that split particles instead of deterministic ones in some sense.
Well, it's a super good question. So okay, it's not what people would do. Also, you could say they add noise. So in practice, at initialization, the thing is going to be very well ill-behaved. So if you run several time transformers, you would actually see several particles evolving. If you want to convince practitioner, you would have to show that it works better. Okay, because here you see all the vector fields, they are smooth. So really you maintain the same number of tokens, so you don't have like diffusion. I think it would be interesting, but I think the first step would be to do a proof of concept that it would help in practice. But you're right, this would be, I think, something to study. I will probably ease the mathematical analysis because we would have some diffusion, so it would be probably much simpler to study.
Thank you for the nice talk. What structure the matrix Q and K have in the train neural network? Do they have some? Do you see some patterns on low rank structure, or they are? I don't know.
So okay, so maybe we should discuss this after, but yeah, I mean, it's very hard to understand what should be good rules, but I think you should expect a bit of low rank structure because you minimize over a product. Okay, if you put the QK on the other side, what you would have is you would have a gradient descent on a product, and typically a gradient descent on a product, first of all, it's a product, so it's going to be low rank, but usually you also converge to matrix that could have a even lower rank. So yes, typically, further assuming that Q and K are low rank could be interesting.
Okay, thanks.
Thank you for a nice talk. In the second part of your talk, why is there no Wasserstein flow in the continuity equation?
Say again?
Why is there no Wasserstein flow in the continuity equation in the second part of your talk?
Yes. Sorry.
Yeah, that's right.
So you mean here? Because it's not a Wasserstein flow. So this, in fact, gamma, I mean, in the paper we prove it, it's very easy. You can show that the vector field, if you compute it Jacobian, it's not symmetric. So this is not
a Wasserstein gradient flow.
Yeah, it's not, oh yeah, sorry. It's not a Wasserstein gradient flow. But I mean, the question is why should it be? In fact, you can show that it's a gradient flow for a twist Wasserstein metric. which is more or less what they add here. But the problem is this twist Wasserstein metric doesn't seem to have very good property. I mean, does it address your question? So this is not a Wasserstein gradient. Just
Thank you so much.
if you remove the normalization and you assume V is QK transpose, then it's a Wasserstein gradient. So what kills the Wasserstein structure is this normalization. So what we did in this paper, if you want to know the full story, we realize this and then we say, can we fix it? So what we did with this paper with Michael is we, instead of, you can see this as a Markov coupling, what we did is we replace it with Sinkern solution. So because this coupling is a row stochastic, we replace it by a row and column normalization. We call this SyncFormer, and we saw we would be rich and super famous. Unfortunately, not a lot of people took over. Actually, it was used in practice. In some cases, it actually improves the performance. And then it's a Wasserstein gradient flow because the matrix is symmetric.
So I think we should stop here with the questions.
Yeah.
There will be time later to go on asking questions to Gabriel. Thanks, Gabriel, again. Okay, so we can go on with the second talk of the morning. So we'll be happy to listen to the talk given by Kathy Craig from the University of California at Santa Barbara, and she will speak about the connection of optimal transport and particle physics. Thanks, Kathy.
Thank you very much, Filippo, for the introduction, and thank you so much to the organizers for inviting me. It's such a pleasure to be here in Pisa. So like Filippo said, today I'm going to be talking about optimal transport and particle physics, and this is going to be based on a few joint works with a variety of collaborators. I'll tell you a little bit more as I speak about each project. So my plan for today's talk is to begin by giving some background on the problem in particle physics that motivated these various projects. And this is the problem of jet classification at the Large Hadron Collider. And then I'll talk about three projects that this inspired. First, a project using kind of a well-known technique known as linearized optimal transport to classify the jets. And then more recently, kind of bit more mathematical projects with actually both of them done in collaboration with undergraduate students at UCSB. We have some kind of really remarkable undergraduates. So let me begin by telling you the background, kind of the problem that motivated us. So I think everyone here is very familiar with the Large Hadron Collider, this incredible circular collider at CERN. It's a 26 kilometers in circumference going under Lake Geneva. They're firing bunches of protons together, millions of times a second. And the difficulty of getting these two protons to collide has been likened to if you were firing two needles at each other from 10 kilometers apart, getting them to meet in the middle. So it's really kind of a marvel that this experiment even exists. What I have here is a picture of the CMS, compact muon solenoid detector. This is one of the two kind of major detectors at CERN, this and the Atlas detector. And this is a cross-section of the detector showing all of the different components. You can see that the detector is kind of nested like layers of an onion. And for scale, here's a person. You can actually go tour it and see it underground. It's incredible. And for most of today's talk, I'm going to be focused on a specific component of this detector, which is called the hadron calorimeter, and that's kind of shown here in yellow. Okay, so what is the problem that the physicists are interested in solving, kind of with respect to this hadron calorimeter? So at a high level, what's going on here is kind of two protons collide. And then when the protons collide, they break apart into partons, is what they call them, which is basically composed of familiar things like quarks and gluons, as well as unfamiliar things like W bosons or Higgs bosons. And the partons interact with each other. Sometimes more partons are created. And then after some time, the partons begin to combine into larger particles, hadrons. And it's these hadrons which can be then measured by the detector, the hadron calorimeter. And so the problem as I kind of am illustrating in this picture, often these partons and kind of the hadrons they combine into will be somehow localized in space in something that's called a jet. A single collision can result in more than one jet, but they're interested in classifying kind of the behavior of individual jets that compose the entire collision event. And so the physics problem that they're interested in is kind of understanding how this partonic process, what type of signal it leads to on the detector. And so how can we understand these signals mathematically? Here's sort of a cross-section picture of this cylindrical detector. So the protons collide, partons are created, and then are kind of measured on this cylinder. For the purposes of my talk, these red and blue colors don't mean anything. Just take it as being the same color. And so what these are supposed to represent is where a hadron hit and the amount of transverse momentum that it had where it hit. Okay, so this is like a cylindrical detector. We could unroll it and think of it as like a two-dimensional image where the locations of the dots indicate where hadrons were detected, and kind of the height of the bar represents the amount of transverse momentum. In today's talk, I'm going to kind of be representing pictures like this as follows. So in this case, now the dots represent where hadrons were detected, and the size of the dot represents the amount of transverse momentum. Okay, so here is, for example, the type of measurement you might have taken if a top jet were created, and here if a W boson were created. Yes? Just in the direction of the detector is just what I mean. Yes, normal in the direction of the detector, yes. Okay, so the goal of the problem that they're interested in solving is they want to use these, hadron calorimeter measurements to classify what type of event occurred at the parton level. And there's kind of a few key attributes of these measurements that make optimal transport techniques a natural choice. So first of all, clearly the spatial locations of the dots is meaningful. It means like where they physically hit the detector. Though I would say it's meaningful after some kind of normalization has been done, kind of taking into account translation and rotation symmetries of the problem. Second, you can see that typically these measurements will have minimal overlapping support. And third, they're relatively low resolution. So maybe transverse momentum will be measured at approximately 200 locations. So maybe there'll be at most maybe 200 dots in these two-dimensional images. This is pretty small resolution compared to even low resolution images people look at in kind of image processing applications. Of course, often in optimal transport, applying this to real data, there's an issue of normalization. And so in today's talk, I'm going to assume that the total PT, total transverse momentum in all of these pictures has been normalized to be 1. If you're interested in the normalization question, I can say a little bit more about that later, like how much information are we really throwing away there with that normalization. Okay, so kind of with these considerations in mind, optimal transport seems like kind of a natural choice to say how similar or different these types of measurements are. And indeed, these were the two first works in the physics literature to use optimal transport-based techniques. Comiskey, Metodiev, and Thaler were a group at MIT. And what they did in this kind of jet classification problem is they used one Wasserstein distance to compute the similarity between pairs of images, pairs of these detector readings. And then they applied a k-nearest neighbors approach to classify them. On this, for example, one of the classifications they looked at was trying to classify whether a signal came from a W jet or a QCD jet. And this is the metric by which they kind of gauge the accuracy of their classification technique. This is a ROC curve. And basically, a technique is more accurate if it's higher and to the right. And so here you see the EMD-based approach, Earth Movers Distance, or one Wasserstein metric. That was the red line. Compared to kind of a classical collider observable, here in dotted blue, it was much better. And it kind of approached the accuracy of techniques based on neural networks. But what was interesting is that it was much more interpretable than these neural network techniques. I mean, it's a very, very simple mechanism by which they were comparing these images. So, this was kind of very interesting and attracted some attention in the physics community, but there were some downsides of this initial work. First of all, they're dealing with like 120K images, and we're computing pairwise distances between 120K things. It can take a long time, so approximately 3 weeks on a supercomputer. And even just storing the 120K pairwise distances would be a pain. Okay, so it had great interpretability, but maybe kind of similar computational burden as these neural network-based approaches. And so this work kind of inspired us to instead use a slightly different metric for classifying these events, called this linearized optimal transport technique. And this is a joint work with Nathaniel Craig, who's a physics professor at UC Santa Barbara, Qianji Cai, who is a physics PhD student at UCSB, now doing her postdoc at Stanford, and Junyi Chen, who is a physics undergraduate at UCSB, now doing her PhD at Harvard. And so the idea of this was to use this, beautiful linearized two-Wasserstein framework introduced by Wang, Slepcha, Basu, Ozolek, and Rode. So many of you may be familiar with this, but let me recall it for those who haven't encountered it yet. So the idea of this framework is to leverage this kind of formal Riemannian structure of the two-Wasserstein metric dating back to Otto. So how does this work? So if we have two measures, sigma and mu, and sigma doesn't give mass to small sets, then the two-Wasserstein distance between them can be expressed in terms of the optimal transport map from sigma to mu minus the identity, and then I take the L2 norm with respect to sigma. And so if we think about the kind of Riemannian perspective on the two-Wasserstein metric, if I'm interested in the true Wasserstein distance from a measure sigma to a measure mu, so I'm imagining that the actual Wasserstein manifold is this kind of curved orange manifold, the true Wasserstein distance would be exactly kind of the length of this curve. But kind of as Otto showed, we can think of sigma as having a tangent plane, well-defined tangent plane, and the tangent vector pointing in the direction of mu is exactly the optimal transport map from sigma to mu minus the identity. And the length of this tangent vector in the norm on the tangent plane, the L2 sigma norm, exactly coincides with the length of this curve from sigma to mu. And so the idea of this linearized two-Wasserstein perspective is that somehow if maybe mu and nu are not so far from sigma, one could hope that computing the exact distance from mu to nu on the Wasserstein manifold, which would be the length of this curve, should somehow be approximately the same as computing the length of this line segment in the tangent plane. And so we would get the length of this line segment just by taking the difference of the tangent vector in the direction of mu and the tangent vector in the direction of nu. Okay, so why is this useful? Why is this kind of linearization of the two-Wasserstein metric useful in our case? Well, in our setting, we don't just have two measures that we want to compute the difference between. We have, 120,000 of them. And so that's represented by all these different dots on the orange curved manifold. And so if we were going to compute the pairwise distances between all of these dots on the manifold, computing all of the curves connecting them, this could be computationally intensive. But what the linearized perspective allows us to do is it says, instead, fix a reference measure, sigma, that doesn't give mass to small sets, and compute all of the optimal transport maps from sigma to each of these black dots, each of these other measures. So that will give you, if we have sort of n total measures in our data set, we have to do n expensive optimal transport computations to compute all of those optimal transport maps. But then once we have the maps, we can approximate the pairwise distances between all the measures by just doing a cheap Euclidean computation of the difference between each of these vectors. Okay, so this is kind of the major benefit that I summarized here. So it kind of decreases the number of expensive optimal transport calculations you have to do by an order of magnitude. It's also a metric in and of itself on the space of probability measures with finite second moment. And I have a feeling we'll hear a lot more in the next talk by Quentin about recent work showing the by-Holder equivalence of this linearized optimal transport metric with the classical two-Wasserstein metric. So here's sort of one such result, but there are many others. So it's a metric in and of itself. It is, in some ways comparable to the classical two-Wasserstein metric. Also very relevant from the perspective of applications in this JET classification task is that it provides an embedding into a linear space. We've seen the utility of this many times already in today's conference, that it's much easier somehow to work with the transport maps than the measures themselves sometimes. And in this case, it is also the situation. And what's nice is that if I endow this embedded space with the L2 sigma norm, it's got an isometric embedding on the embedded space, then with the LOT norm on the manifold of probability measures. And once this is a linear space, you have a much richer class of classification algorithms you can apply. And furthermore, you don't have to store the whole pairwise distance matrix between all n-squared probability measures. You just have to store all of the optimal transport, one optimal transport map for each of the probability measures. And then lastly, there was some a variety of interesting works by Mossmuller and Kloninger observing that, for example, the linearized optimal transport metric preserves these nice properties of how two Wasserstein behaves along translations and dilations. And this is simply due to the fact that, we know that in general, the composition of two optimal transport maps is not an optimal transport map, but if it's a translation or a dilation, then indeed it still is optimal. Okay, so I'll say just a very short bit about how we implement this numerically. There's a variety of choices you could make. Here's the choice that we make for this particle physics application. So we take our reference measure. Our reference measure we typically choose just to be a uniform measure on the square of this kind of segment of the detector that we're looking at. Interestingly, we looked at a variety of choices of reference measures, and in our application, they all performed about the same. So if, for example, sigma is the uniform measure, we discretize it as an empirical measure, for example, a uniform measure on a grid with equal weights. And then for each jet, each of our jets are already represented as an empirical measure. We compute an optimal transport plan from our reference to the jet. And then we use that plan to build sort of an approximate optimal transport map. And so basically, we kind of compute this average. And this tells us that if you start at location xi, in your reference measure, what's the average location that mass gets sent from that point? So this gives us an approximation of the optimal transport map, and then an approximation of the embedding into a linear space. And then we define the fully discrete linear optimal transport metric in terms of this embedding. And sure enough, as long as this approximation of your reference measure gets better and better, and that your true underlying reference measure doesn't give mass to small sets, this indeed converges to the actual continuum linearized optimal transport metric. Okay, so this is how we implement it, and how does it perform? So here we compared it against that same task I showed you before by Comiskey, Metodiev, and Thaler. Now the computation of the embedding only takes 6 hours on a laptop as opposed to 3 weeks on a supercomputer. And we also have access to many more types of classification algorithms. So whereas before they considered k-nearest neighbors classification algorithm, since all they had access to was the pairwise distances, since now we've embedded it into this linear space, we can also do things like support vector machines and LDA. And at least with, for example, support vector machines, the accuracy of our classification is comparable to what they were able to achieve with the exact one Wasserstein metric. So this shows that even with this linearization that has these huge computational benefits, you don't get much of a decrease in accuracy. And even if you use kind of like a naive classification method, like LDA, where you basically just kind of project onto a principal component, you still get you know, not too bad of results, and they're can offer a beautiful interpretation. So here we projected those optimal transport maps in the embedded space onto the direction that characterized the maximal variation, and then we ordered all of the jets according to where they lied in that direction, and you can see how it very clearly shows this key distinction between W jets and top jets in terms of the variance of the spread on the detector. Okay, so so this was kind of our first work in this direction. You know, basically just taking this existing mathematical framework and applying it to this data set. But this has attracted some, like now particle physicists are even more excited about optimal transport. And there's been some subsequent works by them that I just want to mention because, yeah, I think it's, especially in the US, optimal transport has not always been so popular. And sometimes, especially during my PhD, when I would tell people I did optimal transport, they would say like, oh, do you design like subway maps or what is exactly that you do? But I really think this connection with physics, suddenly a lot more people have heard about it. So here is another paper by the group at MIT. They kind of realized that this language of optimal transport would be a great way to mathematically formalize some idea they had of something called infrared and collinear safety. So given these measurements, which we think of as probability measures, they like to use those to compute observables, which we would think of as functionals on the space of probability measures. And they wanted those observables to have some good kind of continuity properties or robustness. And they realized they could formulate this exactly in terms of saying that those observables should be continuous with respect to perturbations in the two-Wasserstein metric. And then kind of another observation they made is that they had this notion of something called event shape, which they realized they could pose as saying, given an event mu, what is its minimum distance to submanifold on the space of probability measures. Maybe, for example, the submanifold of all probability measures composed of 4 Dirac masses. And this is a way to kind of quantify the extent to which an event has a certain shape. Okay, so we see it's even kind of having an impact on kind of theoretical particle physics in terms of how they mathematically formulate these ideas. And then here was another paper by my colleagues at UCSB using these same ideas for anomaly detection. And so they would have some collection of standard model events or kind of familiar events which are often observed at the LHC. So we're thinking about each of these measurements as a probability measure on the Wasserstein space. And then they would be given 2 new events, and they would try to determine if they were an anomaly or not. And the method they proposed was pretty simple. When they told me this is what they were going to do, I thought, I don't know if that's going to be good enough to detect it. But basically, all they do is they compute the minimum distance from the new event to the standard model, to the given standard model events. And then they cut based on how close it is to the given standard model events. And this cut is apparently as good as the state-of-the-art methods in anomaly detection. So I think this is really interesting because it's, I think it has such a clear mechanism. And it's interesting that something with such a simple mechanism can perform so well. Okay, so this first project was kind of motivating what is this jet classification problem? Why is optimal transport useful in this jet classification problem? And now, kind of after these initial works, we're looking at a few more mathematical questions inspired by it. And so this first project I'll talk about is about wavelet S Wasserstein distances. And this is joint with Haoqing Yu, who is an undergraduate student at UCSB. Okay, so what was the motivation for this project coming from the physics application? So as I've already said, kind of in physics application, we have this goal of classifying in probability measures based on their mutual Wasserstein distances. And this linearized optimal transport framework reduces the number of expensive optimal transport computations from order n squared down to order n. But of course, if each of these measures and our fixed reference is composed of, for example, m samples, even though we only have to do order n computations, those could each be somewhat expensive, kind of depending on the number of samples. And so this student and I were interested by this result due to Sharon Dakar and Jacobs from, a while ago at this point. This result appeared in the engineering literature. So the statement of the theorem is a bit informal, but here I've done the best I can to kind of capture the spirit of it. And this was the idea of their result. So they were looking at S Wasserstein metrics for S between 0 and 1. So this is where the cost is the distance to the power S, a concave function of the distance. And what they showed was that there exists a wavelet S Wasserstein metric given in terms of a weighted L1 norm of the measure's wavelet coefficients. I'll give a precise formula in a second. And there also exists some constants depending on the parameter S and the wavelet system, so that this wavelet S Wasserstein metric was bounded above and below by constants times the classical S Wasserstein metric. And so why this result was interesting to us from a computational perspective is if you are given m samples from a measure, it only is order m to compute its wavelet coefficient. So this could be a huge computational advantage if it performed well. And we kind of hoped it would perform well because we looked at these original pictures from this paper by Sharon Dakar and Jacobs, and here they computed pairwise distances between a lot of images and some kind of standard data set, and they compared the distance in this wavelet type of Wasserstein distance with the classical 1 Wasserstein distance. They apparently had to scale it, so we knew there was going to be some normalization involved, but after that normalization, things seemed to look pretty good. However, when kind of as a sanity check, I asked the student to check the following example, and this started to make us very worried. So what was the example that he looked at? So he fixed 2 measures, so a probability measure, the uniform probability measure on the interval 0 to 1, and then shifted to the right by some amount A. And he kind of computed the distance between these 2 things as A varies from 0 to 2. In the dotted lines, he plotted kind of the classical S Wasserstein metrics, both 1 Wasserstein, which is of course just a line, and then W1/2 and W1/4. And then he plotted kind of the corresponding wavelet S Wasserstein metrics, kind of multiplying by an appropriate normalization constant. And it didn't look great. I mean, it didn't look impossible that these things could be equivalent as metrics, but it was certainly kind of missing some key properties of the wavelet S Wasserstein metric, or the true S Wasserstein metric, as the supports of the measures were no longer overlapping. So we started to kind of dig in a little bit more into this paper. The main idea underlying this, the definition of their, yes. Let's see. Thank you. Okay. So the main idea underlying this wavelet characterization is, of course, the kind of classical Kantorovich-Rubinstein duality result for S Wasserstein metrics. And so when S is strictly less than 1, we know that the S Wasserstein metric can be characterized in terms of the supremum over all functions whose Holder semi-norm is less than or equal to 1. And this kind of makes the connection with wavelets somewhat natural because there's this classical result due to Meyer saying that a function is F Holder continuous if and only if the approximation coefficients are uniformly bounded by some constant and the detail coefficients are uniformly bounded by some constant up to a scaling factor depending on the level of the detail coefficient and the wavelet, or in the Holder exponent S. So I'm not going to get too much into detail on the kind of background on wavelet theory, but for those of you who haven't worked with this before, how you compute these approximation and detail coefficients is you start off with an approximation wavelet and a detail wavelet, and by looking at integrals of the function against translations of the approximation wavelet, that's how you get all of this vector of numbers. And by looking at integrals of the function against translations and dilations of the detail wavelet, you get this vector of numbers. Okay, so this kind of makes it's clear there's some sort of connection between this optimization problem over this Holder space and maybe optimizing in wavelet space over the size of these coefficients. And kind of the main contribution of this Sharon-Descartes-Jacobs paper was they made this type of result quantitative. So Meyer's result doesn't tell us, for example, how these constants C0 and C1 depend on the size of the Holder norm of F. And so kind of what this paper did was they said, if, for example, the Holder norm is less than or equal to M, what is the worst case for how C0 and C1 can depend on M, and vice versa. Okay, so they made this a bit more quantitative. And so by kind of inspecting their argument, we realized that, you could think of kind of a whole range of these type of wavelet S-Wasserstein distances, and they could be defined as follows. So you have some constants, C0 and C1, they appear here and here. You have some lowest level, J0, which is some integer. And we have probability measures, mu and nu, which sort of rigorously speaking, to make this theory work, let's assume that they have densities in L2. And in this case, one could try to define a wavelet S-Wasserstein metric in terms of this kind of L1 norm, little L1 norm of the approximation coefficients multiplied by a constant, and then the sort of weighted little L1 norm of the detail coefficients going down to level J0. So the original paper looked at a specific case of this. They considered the case C0 equals 0, C1 any positive number, and lowest level J0 0. Unfortunately, upon closer inspection, it became clear that the result was actually not true in this case. This is not actually equivalent to the S-Wasserstein metric. We both have a counterexample, and kind of you can see where the things went wrong in the proof. The good news is it's a very minor fix. Basically, it was just you couldn't require this C0 to be 0, and furthermore, you had to assume that these measures were supported on a bounded domain. And in that case, these constants CL and CU will also depend on the diameter of the domain. So this issue with the domain was probably not even at the front of their mind in this image processing literature, because they're always on some sort of fixed grid. So they were probably very happy to assume they were just like on the cube or something. Okay, so a very mild modification fixes this result. But somehow, even with that mild modification, when we started looking at the behavior of the simulations, it was still not giving us the results that we wanted. It was still not capturing the behavior of the true S-Wasserstein metrics. And so this motivated us to go back one more time and consider a final variant, which is where we again drop the approximation coefficients, taking C0 equals 0. This actually really makes sense from a theoretical perspective, because in this Kantorovich-Rubinstein duality characterization, you could really think of this as kind of dual with respect to the homogeneous Holder space, because of course, like shifting f and up and down by a constant doesn't affect the integral, since mu and nu are probability measures. And Meyer had a characterization of the homogeneous Holder space purely in terms of the detail coefficient. So it really kind of makes sense to drop this term. And so dropping this term, we were able to show that as long as you take J0 sufficiently small, depending on your domain, we were able to almost recover equivalent of the metrics, but up to a small error term. So basically, for any eta, we can choose J0 sufficiently small so that these things are equivalent. But a key downside or a key weakness of this theoretical result is that our constant deteriorates with J0. So we weren't super happy with this theoretical result, but it was somehow kind of the best we could do. But the good news was that the performance numerically was much better. Somehow, focusing instead on the detail coefficients and going down to a low enough level, we were much better able to classify, to capture these properties of the Wasserstein distance. Yeah. Correct. Yes. Yeah. Exactly. Yes. Okay, so kind of in summary, the pros of these wavelet S Wasserstein metrics are the drastically lower computational complexity. Similar to the linearized optimal transport framework that I was speaking of, they still give us an embedding into a linear space, kind of taking the space of probability measures into the space of kind of wavelet coefficients. And so this is nice from the perspective of classification problems. You can, apply these standard classification algorithms in Euclidean space directly to the wavelet coefficients. And it's kind of an isometric embedding, again, in terms of this wavelet S Wasserstein metric. A big benefit of this approach compared to the linearized optimal transport framework is that it's sparsity preserving. So in the linearized optimal transport framework, we're always thinking about our reference measure sigma naught is, for example, a uniform measure on our space. And so then the optimal transport, the optimal transport map from that sigma to some measure mu, even when discretized, is not going to be a sparse vector, because basically there's mass at every point that has to get sent somewhere. On the other hand, if you have some nice compactly supported wavelet system, and you have a sparse measure mu, its wavelet coefficients are also going to be sparse. So this is kind of interesting. We showed that it, at least numerically, captures key behavior of WS under translations and dilations. Like, I only showed you one picture here, but we have many others in the paper. Interestingly, this behaves well as S goes to 1. This is kind of surprising because if you go back to Meyer's kind of classical characterization of S holder functions in terms of the size of their wavelet coefficients, if you take S equals to 1, it actually becomes a characterization of Zygmunt class functions in terms of the size of their wavelet coefficients. So even though Meyer's result kind of degrades as S goes to 1 numerically, we do not see any kind of degradation or blow up as S goes to 1. And it seems kind of robust against the choice of whatever wavelet system you want to choose. But the cons are, I feel like our existing theoretical guarantees are comparatively weak. And I mentioned there's this issue of normalization constant, which is something we don't really understand and kind of had to empirically choose each time. Okay, the last project I'm going to talk about today is actually work in progress with 2 collaborators. Ben Factor, he was an undergraduate student at UC Santa Barbara, just a few months ago began his PhD at UCLA. And Ben Nachman, who's staff scientist at Lawrence Berkeley National Lab and also a member of the CMS collaboration at CERN. And so this was a deconvolution problem via optimal transport. And so the problem that Ben Nachman described to me, again, kind of goes back to this detector that we were looking at pictures of earlier. And so, protons collide and lots of things come out, for example, a muon or an electron, or we were focusing on hadrons, which are kind of shown here in green. And we were looking at the measurements of the hadron calorimeter. And I was telling you a little bit of a simpler story before. We were thinking about the hadron calorimeter as sort of an infinitely thin cylindrical shell, and kind of the measurements as sort of just the locations on that shell. But we can see that in practice it's not infinitely thin, and in fact it's kind of composed of more than 100 million sensors. And it's an interesting problem in practice how to go from these kind of messy readings by all of these sensors to infer somehow where the hadron actually was and the actual amount of momentum with which it hit the detector. And the reason why this is important is because, like I mentioned, there's these 2 different detectors at CERN, both the CMS and the Atlas, and they have very different structure. And so you want to somehow take the detector readings from both of them and remove the detector effects to have like an apples to apples comparison of the actual type of hadrons that were detected. So this is just like a classical deconvolution or denoising problem. And the way we set it up is we have some measurement nu. This is in general some sort of like weighted sum of Dirac masses, like the pictures I was showing you before on the detector. Then we have some noise model. So I'm going to think of this as just like a Borel map from some space X into probability measures on the detector. X and Y will both subspaces of Euclidean space, but they could have different dimensions. Or subsets of Euclidean space. A simple version of noise model that you can have in your head is just Gaussian noise. So maybe think of phi as like a Gaussian with mean 0 and variance 1. And then we have some true data, sigma. And the goal is that if we let nu sub sigma denote the noisy data, so this is just it's the measure you get when you take the data and you apply the noise model. So in particular, in the case of Gaussian noise, it would just be convolving the data with a Gaussian. So if nu sub sigma is the noisy data, the goal in deconvolution is to find the true data, sigma star, that makes the noisy data as close as possible to the measured data, where J is an appropriate notion of loss function, and perhaps you also have a regularizer R. There's many common choices that arise in practice. For example, like an L2 norm, and then a regularizer can be like a TV or even L2 norm, or so maybe even a Sobolev norm or inverse Sobolev norm. And then what actually shows up often in a particle physics application is a KL divergence. And the state of the art that is done in this context, the scientific context, is that they'll try to find the sigma which minimizes this KL divergence. And they do it by doing a gradient descent of the KL divergence with kind of cleverly chosen time steps. And this is called Lucy Richardson technique. But a major downside of maybe these common choices is that, especially if we're thinking of nu as just a probability measure, like a sum of Dirac masses, you can't really evaluate like a L2 norm or KL divergence without some sort of binning. And this introduces kind of additional layer of approximation and inaccuracy to the procedure. So they were interested in could we use optimal transport to do sort of a binning-free approach? Yes. So what I mean is that, like, imagine that, so you have nu, which is an empirical measure, and then maybe nu sigma has a density with respect to Lebesgue, so it's convolved with the Gaussian. And then you want to compute the KL divergence between them, but one is not absolutely continuous with respect to another. And so what they call this for binning is maybe they will lay down a grid and then approximate the empirical measure by characteristic functions on the grid or something like this. A very confusing thing about this project is I'm working with two people named Ben, and our goal is to do this without binning. So we have conservation of bens, since we have the bens in the author list and not in the method. Okay, so kind of a natural approach would be to instead choose your loss function, for example, B2 Wasserstein. And things like this have been studied before, especially there's been a lot of work on inverse problems by Yunnan Yang and her collaborators, including Dunlop and Inquist. Though they were looking at, what played the role of their noise model could be kind of nonlinear. So our setting is quite a bit simpler since our noise model is linear. Indeed, we were able to show that this problem makes sense. So for example, as long as the infimum of this over all sigma is finite, as long as our noise model is continuous with respect to narrow convergence, and that as you vary x, the second moment of the noise model has, for example, compact level sets, then you can ensure a solution exists. And then, okay, maybe in many cases you don't expect the solution to be unique, but as long as your noise, taking a sigma and applying noise to it is an injective mapping, and for example, nu didn't give mass to small sets, you could show the solution is unique. Okay, so this is a reasonable problem, but the key difficulty, of course, with things involving Wasserstein metric is how do you use it in practice? So the good news is if we kind of just write out the definition of 2 Wasserstein in terms of optimal transport plans, gamma, we can recognize that this is again a linear program. It's the objective function depends linearly on the transport plan, and we see that these constraints are linear in gamma and sigma. So this is fine. This is a linear program. You could solve this directly, but you would get bad behavior. Well, we did because, of course, like for example, if you have a Gaussian noise model, you can know everyone can see that you can have very different values of sigma that once you convolve them with the Gaussian appear very similar. So there's this kind of intrinsic instability. And so this is, of course, why everyone adds in kind of a regularizer when they're solving this type of denoising problem. A natural candidate in this context was to regularize by penalizing the entropy of the measure sigma. And then for numerical reasons, it was also very favorable to penalize the entropy of the transport plan gamma. And the reason why is because then it turns out this is exactly, this type of problem can exactly be solved by generalization of the Sinkhorn algorithm, exactly this type of matrix scaling algorithm. So this is what we did. The only wrinkle is we have to, one of the operators we have to compute while solving this algorithm is a proximal operator with respect to the kernel of some matrix B, depending on our noise model. And this does require inner iterations. So that's a downside compared to kind of the classical Sinkhorn algorithm for just computing 2 Wasserstein, for which the analog of this just has like a closed form expression. Just a proximal operator on an indicator function on a single vector. So I'll close with just 2 quick examples. So this is an example that my collaborator, Ben Nachman, looked at in a paper published in Nature Quantum Computing. They were looking at a model of noise coming from these types of quantum computing machines. So the true data, it was shown in black. The noisy data or the measured data was shown in gray. And what this paper was all about was using the Lucy Richardson technique, shown in orange, as kind of an approximation to go from the measured to the true. And sort of what I wanted to convey by here is that our optimal transport technique in this example is very similar to the Lucy Richardson, but you can also come up with other examples where it does much better. So here, our true data in black is given by this kind of double bump. Our measured data, once we apply the noise, so it's Gaussian noise with a rightward shift, is shown in gray. And we can see here that in purple, the optimal transport deconvolution is much closer to the black than the orange, the Lucy Richardson. So this is work in progress. These are just some toy examples. But this is, again, just showing how these types of optimal transport techniques are now kind of becoming more popular in this particle physics application. So there's several directions for future works, but since I'm already a bit over time, I think I'll just leave it here. Thank you very much.
Many thanks, Katie. Do you have questions for Katie?
So for the wavelets, you use like orthogonal wavelets or something like this, right?
And so we were just doing this in 1 dimension. Yeah.
And did you, because I did my PhD in wavelets a long time ago. And so for denoising, what people were using is more like translation invariant wavelets, which means that instead of having like linear time algorithms, they have n log n, but the advantage is it's invariant to shift, but the wavelets are not invariant. So I'm wondering whether this could improve a bit the results.
Yeah, so just to make it clear, so I think I talked about 3 different projects. So for this last project, we were not using the wavelet approximation, but for the middle one.
No, I mean for the middle
exactly. So, and I mean, this even gets at another thing that I think we're interested in. So, so I think the choice of wavelet system is clearly very interesting and may kind of give this sort of wavelet-Wasserstein metric different properties. So even in just kind of the original jet classification problem, we have to do this sort of normalization step where we translate the two jets to have the same center of mass and rotate to have the same principal axis. So in 2D, these types of normalization steps are fine. Like it's not too bad to do. But I think to me, it's a very interesting question. If you're wanting to use optimal transport on these classification problems in higher dimensions, what's an appropriate way that you can make them invariant with respect to certain symmetries of the physical problem? And I think this is a way in which, perhaps bringing together these two ideas, these wavelet techniques, could help.
And when you say higher dimension, what do you have in mind? What would be the dimension?
3 dimensions. I
Dimension.
mean,
I think 3D is also okay for wavelets. I mean,
well, but yeah. So, but I was gonna say the the symmetry invariant is So maybe wavelets could be a nice way of incorporating the symmetry invariance to 3D. Yeah.
Okay, thank you. It's very nice.
Hi, really nice talk. At the beginning, you say that you use the Wasserstein one distance on the 2D images, right? By one, don't you try to solve it directly on the cylinder?
So this is I'm so glad you asked that, because this is something else I didn't get to talk about. The first part of my talk, especially when I was mentioning the original work by the group at MIT using the one Wasserstein metric on these images. Here we were focusing on the jet classification task. So a single collision will give rise to many jets, many sprays of particles. And these jets, well, I can try to go back, it'll just take a while. They then have a standard algorithm for kind of clustering these jets. So let's come back to this picture. Yeah. So there might be several different jets, and then they will kind of cluster them or kind of cut out the image. And so they're actually doing the pairwise comparison of all of these different jets across many different collisions. So it's not a full event level classification where an event may be composed of many different jets. In fact, we've also worked on this problem, and we have a preprint coming out later this month, where we try to instead represent an event as kind of a weighted sum of events and basically do OT on OT to compare things at the full event level.
Yes, because I was also thinking that for the Wasserstein one distance, there are efficient algorithms based on essentially the work again on Jacobs that use essentially the computational bottleneck is just using Fourier transform. So it's extremely fast for just computing the Wasserstein one distance in a 2D image. So did you consider that?
So I guess the reason we didn't consider that, but maybe I should think about it a bit more, is because we really wanted to not have to compute pairwise distances between all 100,000 images. And so having this kind of linearization was important to us. This is something that was present for the linearized optimal transport of W2 and also in the wavelet approach. Yeah.
Okay, thanks.
Thank you.
Okay. I think it's probably better to stop here because we're a few minutes out of schedule. So let's thank Katie again. Okay, so welcome back to the third talk of the morning. So before introducing the speaker, just a technical announcement. Some technicians have been called to let the room be less cold. We hope that it will work. Okay, so it's a pleasure to introduce Quentin Mérigot from Université Paris-Saclay and the École Supérieur, who will give a talk about gluing methods for the quantitative stability of optimal transport maps.
Okay, so thank you, Filippo, and of course, thank you to the organizer for setting up this super nice workshop. So I'm going to talk about actually two different works. So the first one is with Alex Delalande, who was a PhD student at the time, and Cyril, and the second is with Cyril Le Truit, who recently joined Orsay. So I'm going to talk about stability of optimal transport and quantitative stability. Well, of course, just to fix notations, I'm going to work only in the case P equals 2 on RD. Rho will always be absolutely continuous with respect to Lebesgue, and mu will be another measure which is not necessarily absolutely continuous. So in this case, we know there exists an optimal transport map given by the gradient of some convex function. I will denote it T rho to mu, And the convex function, I will denote it phi rho to mu, and I will assume that it has a 0 mean. And in all the cases that I will consider, phi rho to mu is uniquely defined because the support of rho has some connectedness. Okay, and so the question that I'm going to talk about is the stability of the maps. So rho is fixed, and I'm changing the mu, so I'm looking at the optimal transport from rho to mu, and I'm changing mu, and I want to know how this impacts the map, the change of the map. And the same question for potentials. And this is, I think, a very fundamental and natural question in optimal transport. And actually, my main motivation, my original motivation was related to the talk of Cathy Craig about this linearized OT business. And but let me just give a few more other motivations. So the first one is about the understanding maybe the stability of geometry of Wasserstein space. And in particular, a natural question is if you take one geodesic and you change the endpoints, how does the geodesic change? It's very natural and it's related to this question. And you can ask the same question about Wasserstein barycenters. Then the second motivation is related to this linearized OT settings that I will explain again a little bit later. And the third question, which is also very natural since there are a lot of applications of optimal transport, is that in applications, you never consider the continuous problem, you always discretize. And there is some assumption that this discretization is harmless, so people believe that there is some continuity of the transport map as a function of the data. And we will see, the question that I will address is this map Hölder continuous as a function of mu? And let me start with Wasserstein geodesics again. So I will denote the geodesic or the displacement interpolation as rho mu at t. So this is a geodesic between rho and mu at times t. And there is a very simple lemma that shows that if you want to control the distance between the point at time t between rho mu and rho nu, it is less than t times the L2 distance between the transport maps. It's just because you can use this to construct a coupling between these two measures by an explicit construction. And the point is that without assumption on the source rho, this midpoint of a geodesic can be discontinuous. So for instance, if rho is these two red points, mu is the blue points, then you change a little bit mu, they cross the mediatrix and then the geodesic changes a lot. So you cannot hope for continuity of geodesics, so you cannot hope for continuity of maps as well. And actually, this is a discrete phenomenon, and it's due to the lack of uniqueness of optimal transport map in that case. But actually, it's possible to just make this a little bit fatter, and you still get a very bad continuity behavior, even though there is uniqueness of the optimal transport map. It means there is uniqueness, but uniqueness is not so strong in some sense. And so the new question is what properties of rho will make the transport map from rho to mu continuous in mu? Okay, so the second motivation is this linearized OT setting. And Cathy told you a lot about this, so I will be a bit faster. And the idea is related to the Riemannian geometry interpretation of optimal transport. And the main idea is that you can consider the transport map from rho to mu minus identity as a logarithm in the sense of Riemannian geometry of at rho. And so in statistics, people use this all the time. They want to do statistics on manifold. They fix a point on the manifold, they work on the tangent space, and instead of working with points on the manifold, they put them back to the tangent space using the logarithm. So linearized OT is really doing this on the optimal transport maps. And so it provides an embedding from mu from the Wasserstein space to L2 space, which is injective. And you can embed your data in the L2 space and then work there, which is much nicer. One point that I would like to make just here, because it was not highlighted in the previous talk, that one very nice feature of this embedding is that the image of the embedding is convex. because the set of gradient of convex function is convex, which means that if you embed data, you take convex combination, then it is still in your image, which is a very nice property. Okay. And just as an illustration, you can try to do a linearization of the barycenter problem. So the barycenter problem is this one, the one introduced by Guillaume Carlier and Martial Aguet. And the downside of this problem is that as soon as, if you want to change the alpha I, at every time you change them, you have to solve a new optimization problem. So computationally, it's quite heavy. If you work in the linearized Wasserstein space, what you do is that first you embed your data in the L2 space by taking the transport maps. Then you take a barycenter in this L2 space. And then to go back to probability measures, you take the image of rho under this average transport map. And you get a simple expression. And if you draw pictures of barycenters, so I think the 4 points are this, and this. And you have seen similar pictures for real Wasserstein barycenters. They look similar. So it's, for application side, it's probably a good replacement. But then the question is, what amount of the Wasserstein geometry? Yes. Oh, yes. Okay, that's true. Yeah, multi-marginal problems. I mean, the number of unknown explodes as you increase the number of margins. So I don't think this would be feasible, but this is true. And so the question again is, what amount of the Wasserstein geometry is preserved by this embedding? Okay. Yes. 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 These are the linearized Wasserstein barycenters. So this is a linearized Wasserstein geodesic. This one as well, and okay. This the reference measure I think is 0 Lebesgue on the square. Okay, so now I would like to discuss stability issues again, and starting with the case of rho being bounded from above and below on the convex set. And let me start with what I call local results. And the first point that I want to make is that first it is, well, the map, when rho is absolutely continuous, this map is always continuous, but it is in general not better than one half folder. And actually it's very easy to build counterexamples, very simple counterexamples, where you don't get better than one half folder. So the first theorem that I would like to mention was this theorem of Ambrosio and Gigli, which says that assuming that your transport map from rho to mu is lambda Lipschitz, then you can show that the transport problem, the transport maps are stable close to mu. Yes. And as a function of x. Yes. Yes. So you say I'm in a setting where the transport map is regular, and then around this situation, I get stability. And the stability is one half folder, so this matches this counterexample. This is quite nice. One other nice thing is that only this map is assumed to be regular. So this map can be, for instance, piecewise constant if mu is discrete. So this is something that is applicable in statistics or numerical analysis. And maybe the downside is that the hypothesis that this map is Lipschitz, if you want to establish it, you need to use the regularity theory for optimal transport. So you need a very strong convexity assumption on the support of the source, the target, and then some assumption on the densities as well. And actually, this can be improved to actually not one half folder stability, but Lipschitz stability, assuming that not only is the transport map Lipschitz, but actually the potential is strongly convex, the Brownier potential. And it is by Lipschitz, yes. And these results have been used a lot in statistics for estimating transport maps or in numerical analysis. And then I want to present what I call global results. So the difference is that we do not assume any regularity. We are not around a single situation rho mu. It's really a global result in the sense that we say that this map that maps mu to T rho to mu will be alpha holder on on the set of quality measures supported on some ball. Okay, and in order to do this, we need to require that the density rho is bounded from above and below on a compact and convex set. Sorry? This is the L2 norm here, and here this is Wasserstein 1, which is weaker than Wasserstein 2. So, okay, so the first result of this kind was proven by Berman in 2018, and the exponent that he got was 1 over 2 to the d, roughly. And this was using complex geometry techniques. And motivated by this, we looked again at this problem using this time convex geometry, convex analysis, and we got 1/6 exponent. And actually, so there is a open question: is what is the best exponent that what you can hope for? We know it's between 1/2 and 1/6, and I have no clue of what is a good one. I've tried to optimize on both sides, and this stability theory was recently extended to optimal transport map for a p cost for p strictly greater than 1, but the exponent is not exactly the same then. And finally, still with Alex, we proved that instead of working with probability measures over the ball, we can work on larger sets. For instance, probability measures whose moment of order p is less than r to the p, when p is large enough. So in particular, p should be larger than the dimension. So actually, you could wonder whether maybe being more clever, you can embed the whole Wasserstein space. You can show that this is alpha holder on the whole Wasserstein space. And actually, there is a very strong negative result that I think was not so remarked in the OT community by Andoni, Naor, and Neyman, which says that if you are on dimension greater than 3 and p is strictly larger than 1, it is impossible to find an embedding of the Wasserstein p space over Rd into any LQ space. And the coarse embedding, for instance, is forbids beholder embedding. And coarse is a very rough, so it's a sort of uniform continuity, and even it's up to additive constants in the inequalities. So it discards. Basically, you cannot hope to get a global holder embedding, but it's even worse than this. Q can be anything, and actually, I'm not very familiar with this type of literature, but it's for any space with non-trivial Banach type, or this is a very general type of spaces that are forbidden this way. Okay, so this puts a limit on what we can hope to do anyway. So now let me come back to the statement, and I will just highlight the main ingredient. So again, we have a density that is bounded from above and below, and we get this 1/6 holder behavior. And actually, this will be, yes, it holds as well, and we will use it later, not assuming that the density with respect to Lebesgue is bounded from above and below, but that the density with respect to some log concave measure is supported from above and below. And the main tool is what I call this Kantorovich functional, which is also sometimes called the semi-dual. And it appears in the dual version of the optimal transport problem, the quadratic optimal transport. But instead of writing it with a square norm, you write it with a scalar product. So this is a maximization problem, and the dual problem will be a minimization problem. Okay. So this is a very natural functional in this setting. And actually, let me show why it allows you to solve optimal transport. And maybe one word, I came to this doing numerics, because this is these semi-discrete techniques I've been introducing rely a lot on this functional. The point is that if you look at the gradient of this, as a function of psi. We will compute the gradient. So first we use the Fenchel-Young inequality here to replace psi star. And then we say let's change psi by psi plus TV. Then differentiating in this inequality, so we are differentiating a maximum. So this is the value of the differential of the function at the maximal point. So this is the differential of this at grad psi star. So I get minus v, because here the differential is v, minus integral of v of grad psi star 0. Okay, so this is a small computation to do. But then, what does it tell me? It tells me that I can write it as integral of v against grad psi star push forward rho. So this tells me that the gradient of k rho of psi, seen as a measure, is minus grad psi star push forward rho. Okay. So this is an important, simple computation, but very important. And then using this, I can rephrase optimal transport, because I know that the dual problem in optimal transport in this setting amounts to minimizing integral of psi star d rho plus integral of psi d mu. And I write the optimality condition. It's a gradient of this plus mu equals 0. Gradient of this is minus grad psi star of rho. So the condition is grad psi star of rho is equal to mu. And then what I obtain as a consequence is that if psi is a maximizer, then grad psi star is the Brownian map. And it's the gradient of some convex function. Okay, so I recover the Brownian map on the source space by solving an optimal maximization or minimization problem on the dual space, on the target space. Okay. Okay, so then the next point is that this is a convex functional as a function of psi. And then it tells me that by convexity, the gradient has some motonicity properties. So grad k rho of psi 1 minus grad k rho of psi 0, scalar psi 1 minus psi 0 is positive or null. And actually, we'll see that not only do we have convexity, but even strong convexity. And strong convexity will imply stability. Okay. So for strong convexity, so this is actually maybe the most interesting part in the paper with Alex, because this is the theorem that you can actually reuse if you want to do variants of the of stability. So I put all the constants here because they will appear later. So not only is this positive, this scalar product, but it is bounded from below by some constant times the variance with respect to rho of the difference of the Brownian potentials. Okay. So it's a bit weird. It's not strong convexity in the usual sense. In the usual strong convexity, I would have here some L2 norm of psi 1 minus psi 0. But then L2 with respect to what? Because I'm in the target space. The measure in the target space is changing. So it's not clear which one to put. So actually, I'm measuring the strong convexity using a L2 norm, but in the the source space. So this is why I have this Legendre transform here. Okay. Okay, so then I will show how this theorem implies stability. It's maybe the easiest part, but okay. So then I take two measures, mu0, mu1. I take their dual potentials, psi 0, psi 1, so the ones that live on the same space. Then if I take the Legendre transform of the dual potential, I get the Brownian potential whose gradient is the Brownian map. Okay. And then I use the strong convexity inequality. So I can control the variance between psi 1 star minus psi 0 star using this scalar product. And then I recall that grad k rho of psi 0 is minus grad psi 0 push forward rho. And by assumption, this is mu0. So actually, this is mu0 minus mu1 minus mu0, scalar psi 0 minus psi 1. And then I use Kantorovich-Rubinstein. I get the Lipschitz constant of psi 0 minus psi 1. times the Wasserstein-1 distance between mu0, mu1. And then, since I'm in a compact setting, the Lipschitz constant of the potential on the target space is less than the diameter of the source space. And then this gives me that the difference between the Brownian potential squared is controlled by the Wasserstein-1 distance. Okay, so I get 1/2 folder stability of Brownian potentials. Then I want to go from stability of potentials to stability of transport maps. And then it's a second inequality that I won't detail at all, but which makes it possible. It's a sort of reverse Poincare inequality. You want to deduce stability of gradients from stability of the functions. In general, it has no reason to be true, but here we are working with convex functions, so it is actually true, and there is a second inequality which is tight. And then if you have 1/3 times 1/2, you get 1/6. Here you have 1/2 holder. If you have a 1/3 holder, so overall you get a 1/6 holder stability. And so this is why the proof is optimal in some sense. The proof is two inequalities. Both inequalities are optimal, but maybe the strategy is not optimal. Okay. Okay. And then I want to move on to another topic, which is for a long time, we thought with Alex that actually we could only hope to get stability when the support of rho is convex, that it was a very strong hypothesis. And actually, we realized in a discussion with Alex and with Guillaume Carlier that actually everything works, even if you take a finite union of convex sets, provided they overlap sufficiently. And let me just show the argument with two convex sets. So we use this inequality here. So we have two measures. Maybe do a picture. So we have ρ1, ρ2. And they are both on convex sets. They are bounded from above and below. But of course, if I take 1/2 ρ1 plus 1/2 ρ2, its support is not convex. But for each of the measures, we have this inequality. Here, it works for any function, any continuous function on the target space. And one very nice feature of this inequality is that the first part is linear. Okay, and this is what makes everything work. And so if we take rho to be 1/2 of ρ1 plus ρ2, we sum these two inequalities. And then we can control exactly as before the strong convexity of the contour functional. But here, instead of having the variance with respect to rho of psi1 star minus psi0 star, we get the sum of the variances with respect to ρ1 and ρ2 of psi1 star minus psi0 star. And then the question is, can you control the variance with respect to rho from the sum of variances with respect to two measures that define rho? Of course, not if the support of ρ1 are disjoint. You cannot hope for anything like that. But if they overlap sufficiently, then yes. And actually, you can show this type of inequalities, and the constant will depend on how much your two sets overlap. Okay. And combining this inequality, we get exactly as before, strong convexity of K rho. And then the second part of the proof, strong convexity implies stability, applies exactly the same. Okay. And then the question was, can we hope to do, what can we hope to do when we have more than two, or actually, yeah. And so let me now try to explain what happens when you have more than two convex sets. Like I will take a finite number of convex sets, but in the end, I think all of this works always as well with the infinite number because the constants do not depend on the number of sets. Okay. So Qi are compact convex sets. I assume that the covering that I obtain this way is locally finite. I control the number of intersections of each Qi with each neighbor Qj. And second, I need to control the, let's say, the ratio between the supremum and the minimum on each of the convex sets. And then, so I have this covering. I can associate to it a graph by joining two convex sets if they overlap. And this is a weighted graph because Wij will be equal to the mass of the intersection between Qi and Qj. And on each vertex, I will put a weight which is rho of the corresponding set Qi. Okay, and so to this graph, there is a naturally associated Laplacian, which is defined this way. And the point is that the eigengap of this Laplacian measures, in some sense, the connectedness of the graph induced by the Qi's. And the eigengap here is just defined using it's defined this way. And the point is that the norm is weighted by delta. So this is why we don't see the dependence in the number of points, actually. It's weighted by the sum of the delta is always less than A times 1 because of this property. Okay. And then if you adapt techniques from spectral graph theory, you can show that you can control the variance of some function with respect to rho by some constant, which involves the spectral gap, times the sum of the variance of f with respect to the rho I. Okay. And then the idea is just to say we want to show strong convexity, a strong convexity inequality. We will use a strong convexity inequality for all of the rho I. And then because we have this inequality, we will control the variance of the difference with respect to rho. Okay. So this is one first generalization to a finite union of convex set. But every time you want to apply this, you need to compute an eigengap of some graph. Okay, and then in the remaining time, I will discuss applications of these ideas to proving new stability results. The first one is the stability results when the support of rho is the whole space and not a compact subset. In the following, I will always assume that the target is compactly supported by simplicity. So the first result is about log concave densities. So rho is e to the minus u minus f, where d2u is greater than kappa identity, so it's a strongly log concave. And f is an infinity perturbation. So if under this assumption, you can show that the potentials are almost 1/2 Hölder in the measures. And the transport maps are 1/9. Actually, it's even 1/8 minus epsilon for all epsilon strictly positive, but then you have a constant that depends on epsilon. And it's probably not sharp as before. And here, actually, I'm lying a little. I don't use any gluing. It's just using the stability with respect to log concave density on banded support from Dario Trevisan and Octave Michler, and using some truncation techniques to get to RD instead of just compact sets. Here, it's this theorem here will use the ideas that I've presented before. So here, it's not, I consider a density which is not log concave. So it's still, again, a perturbation, E minus F with F in L infinity, of some density, which is roughly norm of X to the minus beta, with beta strictly greater than D plus 2. So it is a density which admits second order moments, but which is not log concave. And then we get again stability with exponents which depend on beta, D, and so on. And I won't discuss too much the exponents. And maybe one point that is a bit that was a bit surprising when we noticed it is that, well, first of all, they are not log concave, but actually these densities, they do not satisfy Poincaré-Wirtinger inequality. And the point is that the stability of potentials cannot be deduced from the stability of transport maps. Because you don't have, usually stability of potential from stability of transport maps is obvious because you use Poincaré inequality. Here it's not the case. And the proof technique, I will just be very fast, just explain how to construct the covering. first of all, we will truncate everything to a ball in order to have some compactness. And then this ball, we will cover it by sets, which are quadrants intersected with, quadrants. First, you take a quadrant, you intersect it with a corona, and then you take the convex hull, because you need convex sets in the end. And the point is that the corona are chosen in such a way that the density inside the corona is almost constant, because we want it to be bounded from for the ratio between the max and the mean to be uniformly bounded. So this is why we have these 2 to the g plus 1 and 2 to the j here. And we also have one of the sets is not a corona, is the ball. And the reason will be obvious after why we need this. So we cover our domain with this convex set. And this covering, we can check that it is of type AB with A some constant. So this is the maximum overlap, number of overlap between each of these pieces. And B is a ratio between the mean and the max. And now we can look at what is the dual graph. And if I look only at what happens outside of this ball, I get so these coronas, they both overlap 2 by 2. So I get a straight line, a discretized straight line. And then the ball here, B02, will intersect more neighbors. So we have some complete graph here. And as you can see, this graph is connected. So you can imagine that you can control its eigengap. And actually, it's possible. You can get an uniform lower bound on lambda 2. And then applying the previous result, you get stability from this density. Yes. Okay. And then the last point that I want to make is stability with respect to densities which are not over the whole space, but over subspaces which are not convex. And actually, so we will show stability when the support of when rho is bounded from above and below on some domain. So the class of domain that we consider is a joint domains, but this includes, in particular, Lipschitz domains, or it's a very general property. So a joint domain is some connected bounded open set of RD, such that there exists some point which is called a central point, such that if you take any point in the domain, you can connect it to the central point by a constant speed curve, which has length less than beta. So this is a uniform upper bound. And second, you want that the distance to the boundary increases linearly. And this was introduced by Fridjson in the 60s. So they, as I said, they include bounded Lipschitz domains. They also include domains with some interior cone properties. But they also include some domains which have fractal boundaries. So it's a quite general property, like the interior of a Funclor snowflake. Okay. And there is a theorem that was proven in the late 80s, which shows that joint domains, they satisfy Sobolev Poincaré inequalities, so particular Poincaré-Wirtinger. And actually, there is even a converse, which says that roughly the notion of joint, a domain is joined if and only if it satisfies the Sobolev Poincaré inequalities, if you add some other assumption on the domain. So in R2, the additional assumption is that the domain should be simply connected. So what we are able to prove is that if you take a joint domain, a density which is bounded from above and below on a joint domain, then you get stability of potentials. And if in addition you assume that the boundary of the domain is rectifiable, you get stability of the transport maps. Okay, and with the same exponent as before. So the first point about whether this joint assumption is necessary, the first point is that the uniqueness of potentials, they require some connectedness of the domain. If you have two parts of the domain which are at positive distance, then you cannot hope to get, you don't have uniqueness of potentials. And it can be seen just taking the identity. You can write it as the gradient of different convex functions. The techniques that we use here, they do not only apply to densities that are bounded from above and below, but also to densities that can explode near the boundary of the domain, but in a controlled way, like explode like a polynomial. So in particular, we can deal with a case that was considered by Marc Calin and co-authors about construction of what's called Monge-Kantorowicz quantiles. It's a density that on the unit balls that explode at the origin. Okay, and stability of OT maps. So the second result can be extended to to finite union of joint domains which are not connected. Okay, so to get stability of potentials, you need connectedness. To get stability of maps, you don't. But here it's only a finite union. And actually, the proof relies on a covering of joint domains which was introduced by Bowman, and which was used also in the proof of Bojarski. So let me just introduce the Bowman covering. So you have a domain X with a density rho. And we'll say that it satisfies the Bowman chain condition if X is covered by a family of cubes, F, which satisfies for some central cube, which plays the role of the point x0 in the definition of joint domain, and some constant A, B, C greater than 1. So the first property is that if you take the sum of the indicator function of some slightly enlarged cubes, then it's less than A times the characteristic function of chi. So it's saying that the covering sigma f, where you enlarge a little bit each cube, it is locally finite. And then there is a condition which is similar to the joint condition, is that for any cube in F, you can connect it to the central cube by a path of cubes, such that if you take two consecutive cubes, they overlap in some quantitative way. So the intersection is less than the maximum of rho of qj, rho of qj plus 1. Second, you want the consecutive cubes to be comparable in size. And finally, you want the cube Q to be included in B times Qj for all J. So in some sense, it tells you that the closer you go to the center, the bigger the cubes. And let me just illustrate this. And to show what is a Bowman covering, it's actually not so complicated. So first we start with what's called a Whitney covering, which is a dyadic covering of the domain by cubes. And then to get a Bowman covering, we just enlarge cubes by 1 plus 1 over 10 or something like that. So we get another covering where the cube overlaps this time. And this is the Bowman covering. And then we have, as you can see, there is the cubes in the middle are much larger than the cube on the side. This is the property that I alluded to. And we have a graph, and our result is really something about the connectedness of this graph in some sense. Okay, and there is this proposition from Bowman, which says that if X is John, then X with the Lebesgue measure satisfies this Bowman chain condition. Okay. And what we proved is that assuming this Bowman chain condition, and assuming that rho satisfies some doubling condition, which is necessary in the proof, and which actually forbids us to treat with all type of explosion near the boundary. This doubling condition, it restricts what type of density we can control. So we assume this. So it's a doubling condition only with respect to cubes that belong to the family. Okay, and then what do we get under this assumption? We get that the variance of some function is controlled by the sum of variances of this function restricted to the cube. And this is all we need to apply the stability techniques on the cube and to deduce stability on these joint domains. Okay, and actually this variance inequality, you can also realize that it implies that rho satisfies the Poincaré-Wirtinger inequality, because if you apply Poincaré-Wirtinger there, it's a cube, it's very simple. You sum them and you get a Poincaré-Wirtinger on a... Okay. And so using this, we conclude that K rho is strongly convex. using the strong convexity of Kero Q, and then we deduce stability. And then I finish with a counterexample, which is called the room on passage domain. It's a classical counterexample in this business of joint domains. So there exists a domain, X, which is connected, bounded, such that for any probability density on this domain bounded from above and below, the map that maps mu to phi rho to mu, so I'm not looking at the transport map, but at the potential, it is not Hölder. And the X that we take is a standard construction, it's a room on passage domain, so you take union of rectangles, and then you have freedom on choosing the 8 Ri, the 8 of the corridors Hi, and the width of all of this. And if you play a little bit with it, it's possible to show this theorem. A nice point that is a bit surprising is that instability actually does not use very difficult functions. You want to show instability, so you just want to construct potentials, Brownian potentials, such that the image, the convex potential, which are far in L2, but whose image are close in Wasserstein. And the potentials that we consider are very simple. It's just absolute values of x1, the first coordinate, minus t, and x1 minus t prime. This is how we get this not Hölder property. And if you think about it, this construction implies that if you look at the projected 1D projected density, so I denote it rho til, it is a 1D density. So we know that transport maps are stable in 1D. They are Lipschitz stable. But actually, the transport potentials are not stable. Okay, so it's very surprising for me. But in the end, when you think about it, it's not so surprising, but well, it was a bit puzzling. Okay, so to summarize very fast, so we have established Hölder stability of maps mu T-rho to mu, and potentials for a quite large family of densities, bounded from above and below on compact convex set, log concave densities on RD and some non-log concave ones, and densities bounded from above and below on joint domains. And there exist non-joint domains such that you don't have stability of the potentials. Okay, so there are many open questions. I will just list 3 of them. So the first one is, can we hope to get a characterization of the domains such that you get this Hölder stability property? We know that they include joint domains. We know that there exists some non-joint domains that do not satisfy this property. What is the limit that we can hope here? It's not very clear. Another question, which maybe is more important, I would say, is to understand what happens when rho and mu are discretized. Here, I would just told you what happens when you change mu, but you keep rho fixed. And this is maybe in terms of geodesics, I'm fixing the starting point, but I change the endpoint and I get stability. But then in numerics, very often you discretize both the source and the target. And then you would like results saying that if I take any transport plan, optimal transport plan between rho prime and mu prime, maybe I could hope to control the Wasserstein distance between this transport plan and the transport plan induced by the transport map as a function of Wasserstein distance between rho and rho prime and rho, this is mu and mu prime. Okay. And actually, so such inequalities are proven in Linochetto under the Ambrosio-Gigli assumption that T-rho to mu is Lipschitz. But our proof techniques, I don't think it allows us to guess this type of result. And finally, a very natural question is how much can you extend this theory to other costs besides the norm to the p? For instance, on Riemannian manifolds, cost satisfying Matt-Runninger work conditions. So it's not clear exactly what are the limits in terms of type of costs. And I will stop here.
So thank you, Quentin. Questions for Quentin?
So for John domain, what you construct is a graph that has a special gap somehow, or
Okay, so this is a good question because this is what we tried to do at the beginning, is to use this lemma about
Okay,
graph
yes,
and
yes,
spectra
yes.
graph. But actually, we didn't manage to do so. So actually, the proof of this inequality here does not use the proof that we had before with a spectral gap.
So it's unknown whether there exists a graph with a spectral graph.
It's not clear, at least. Yes.
And also, are there conditions less strict than John condition that would still allow to do the proof, like instead of having like a linear behavior, having some other behavior?
This is a good question. Yeah, it could be possible. There is, I think, a generalized theory where you don't have a linear growth. You have some
Polynomial. Or
I think more square roots. Yeah,
less regular.
Concave behavior. And so I think there exists a theory. I think the main question is whether there exists an analog to this Bojarski theorem in this setting. Yes, I don't know where I put it, but okay. Yeah, okay. Well. Yeah, the main point is that if we are able to use, if such techniques exist for a type of domains, then probably we can translate it to stability routine.
But it's not known.
It's not known, yeah.
I have a question. You use essentially covering with some compact sets and consider intersecting sets, right, with non-empty intersection. I mean, non-empty interior. But is it possible to use convexity of potentials to consider only convex compact sets with intersecting boundaries, yes, and characterize somehow these Chigger constants in terms of the area of the intersection of boundaries, something like that?
So this is possible. So I think what you mean is that in the variance inequality,
yes,
exploiting the fact that f is a difference of two convex functions.
Yes.
Maybe it even is Lipschitz. It could be quite regular. We tried to do it. We didn't manage to. So we actually need the overlap for the proofs, but it's not impossible maybe to get a proof without overlap. Yeah.
Thank you.
There are another question. Maybe we can try to be on time with the schedule, and we thank Kanta again.
Thank you.
Okay, so for the next and last talk of this morning, Daniel Mattes from the Technical University of Munich will give a talk about the discretization of vast and gradient flows with some simple examples and surprising properties.
Thank you so much. So, first of all, thanks to the organizers for inviting me here. It's always great to be in this place, and I try to do something entertaining to bridge the gap to lunch. This will be an easy talk, and that's on purpose. So what I want to share with you is an experience that the four of us here had recently, namely that sometimes when it comes to discretizing Wasserstein gradient flows in space, an easy solution might be actually the best. Yeah? So let me give you a sketch of the talk. So in the heat equation, yeah, that is the easiest parabolic equation that there is. Yeah, that has a lot of nice properties, some of which I'm going to review in a minute, and you can discretize this in an extremely easy way, namely to say you just take central finite differences for the right hand side as a replace an operation here by such a thing, and then although that is so easy, or maybe because it's so easy, this discretization shares a lot of the original properties. And now what we observed is that the same trick works for some nonlinear equation as well. Yeah. So here's a monster that is a DLSS equation. Yeah, with the I'm going to write it in a more compact form later. Yeah, and in this nonlinear first order equation, we do the same trick. Yeah, we replace the second order derivatives with these central finite differences, and all the nice properties that this equation has. Yeah, they are inherited by this discretization. Okay, so that is some of the the main idea of this talk. But before I come to this, let me start with a digression, because I need to explain to you what are the properties that I'm looking at and which are preserved as a discretization. And somehow I have to justify why I'm telling this in front of this audience. There's some Wasserstein involved here. Yeah? So there's a Wasserstein distance. In 1D, you can write it as the L2 distance of the inverse distribution function, but you can also write things in a dynamical way. Yeah? So you take the given rho naught, rho 1, you're looking at all connecting curves, and then you write things out in terms of this continuity equation, and then you're minimizing this action. This gives you the Wasserstein distance. Oh, by the way, that I'm doing things here on 1D does not mean we don't know how to do it in multi-D. It just means I want to spare you from all these indices that come in when you do multidimensional discretizations. Yeah? Right, so this you can do. Then there's a related historically older distance. There's a Hellinger distance, which you can define in this very simple way. That's the L2 norm of the difference of the square root of the densities. And this has a very similar dynamic representation, namely you replace this continuity equation here by simply by an ODE, and you minimize precisely the same quotient. Okay? Now we have one derivative, we have zero derivatives. Now you can guess what's going to be on the bottom here. So there's the same thing with two derivatives. Yeah. Also, this gives you a distance which apparently is new. Yeah. You can think of it as a symmetrized version of martingale optimal transport, if this tells you something. Yeah, just that we are not afraid of backward diffusion. Yeah, so for us, this is completely symmetric. For this distance, we have no closed formula compared to the comparable to the one above, but at least we can prove it is a metric and it has some nice properties. Okay. Let me elaborate a little bit on this last distance here. I'm not going to say anything about the first two. But yeah, so what we can prove about this new distance is that when you go to the one-dimensional circle, that the probability measures on that circle with respect to this metric, that's a complete and geodesic metric space, and the convergence in this metric that is equivalent to weak convergence, and we even have bounds, more or less what you would expect. Yeah, so there are second derivatives coming up, so you can bound this distance here in terms of dual norms of second derivatives from below and from above. So it's a metric. We understand very little about the inner geometry of this metric, so we understand up to now essentially nothing about geodesics. Now we can write down the geodesic equations. Yeah, these are these, and as you can see, there's a nice hierarchy that you have here from the geodesic equations in Hellinger, which is just ODEs. Yeah, geodesic equations in Wasserstein, we have to solve the Hermann-Jacobi equation. Up to this system here, and about this equation, we simply don't know what to do. Okay, there's essentially up to now, there's only one example in which we can compute explicitly the geodesics, and this is for connecting two Gaussians, centered Gaussians of different widths. Yeah, so one is on the left, one is on the right, and there are explicit formulas of how to combine the two. So here you see some of the particle trajectories. Yeah, in the middle is Wasserstein, where the particle trajectories are straight as they should be. Yeah, in the Hellinger distance, okay, the particles do something strange, but maybe the particle trajectories are not the right thing to look at. In the diffusive distance, these particle trajectories here converge, so they are moving on parabolas. That's so far the only thing we know about the geometry. But what we can prove, there's always the same amount of mass in between two. Yeah, it's a quantized precisely. So, but what we do understand, and which somewhat justifies to look at this metric, is there are gradient flows in this metric, and these gradient flows are can be semi-contractive. So, for instance, when we are looking at this potential energy, and we assume that the potential is convex, and it's some strange quotient here that is bounded, then the respective gradient flow, which is this diffusion equation with this modulation here in front, that is semi-contractive in this new distance. Yeah. To D. So I'm all the time. Yeah. So here's the right. So that is the. So it looks like the Wasserstein gradient flow. So we have second derivative, rho times second derivative, and then the derivative of the potential. This gives you this. This gives you this formula. And you can do the same thing essentially for the interaction energy. Yeah. Also here you have a when the potential is convex and some strange quantity is bounded, then the respective gradient flow that is semi-contractive. Okay, that's essentially all that currently I can say about this this distance. Yeah, that's how far we come. And now we are, and I'm going to connect it to the discretization. Good. Digression number 2, discretization. What is the so the discretization? As promised, everything will be very simple. So I take the simplest discretization of probability measures on the circle that there is. So again, I take a fixed number n. I take an equidistant discretization of space, and then I replace the probability density by such a skyscraper landscape. On the skyscraper landscape, I define the usual operations of forward difference quotients, backward difference quotients, and the Laplacian, which is a connection of the two. Okay, which gives me such this 3-point stencil central finite difference. Okay, that's how I discretize the densities, and yeah, well, very canonically, we also discretize Hellinger, Wasserstein, and diffusive transport. So all that we are doing is that in the continuity equation, in the continuity equation, we replace the derivative with a difference quotient, or respectively with a discrete Laplacian, and then the quantity on which we are minimizing, that is still the same quotient. The only difference is here that in the denominator, typically you do not just want to have the rho, but you want to have some kind of average. Yeah. So for instance, here in the Wasserstein case, you would like to average the rho value over two neighboring points. Okay. So that's all I want to say about the discretization. And now the talk begins. Okay. So that is my that is the first example that I'm looking at. That is the heat equation, which you all know very well. And I promise the heat equation has a lot of properties, some of which are now here on the slide. So the heat equation, that is instantaneously and positive global solution, and this solution they form a flow that is contractive in the Hellinger distance, that is contractive of gradient flow type in the Wasserstein distance, and this is contractive in the diffusive distance. Okay, we can prove all these things like initially I did by writing down the computation from Eulerian calculus, or you can be clever and just realize that the solution of the heat equation just means that you are convolving with a kernel, and then you see that by the way in which we define the metrics, they are translation invariant, and they are convex. So if you average two densities, then you can also average the respective curves, and this gives you a smaller value in smaller value in the distance. So just by writing down solution to the heat equation this way, you see that along the solution they can never, the solution always come closer to each other. Okay, that's the heat equation. Now we discretize the heat equation in this primitive kind of way. Yeah, just replacing the second derivative by the central finite difference quotient. And what we find is that also this primitive discretization is a contractive flow in discretized Hellinger, is a contractive gradient flow in discretized Wasserstein, is a contractive gradient flow in the discretized diffusive metric. And the reason for this is, again, that you can write the time evolution also on the discrete level just as an averaging. Yeah? All these metrics are again translation invariant, and you defined everything in a convex way. Okay, so here's no surprise for the heat equation. Everything works. So let's make the things a tiny little bit more complicated. Let's make the consider the second order Peirce medium equation. Yeah, so, and instead of dxx rho, let's consider dxx rho square. Yeah, and this equation has a slightly different properties than the heat equation. It looks like it, but they are compactly supported solutions, such Barn-Blatt solutions, but self-similarly spread in space. But they remain compactly supported, so there's no positivity. And what is known about this equation is that that it has global non-negative solution that form the form of flow, and that flow is contractive, a contractive gradient flow in the Wasserstein distance, and we show that it's also a contractive flow in the diffusive transport distance. It is not contractive in the Hellinger distance. We can easily write down counter example where the solution diverge. Okay, well that's a situation for the PME. Now we do precisely the same thing as before. So we replace on the right hand side the second derivative by this discretized Laplacian. Yeah? And then you see when you solve this that you have instantaneously positive solutions that form a flow, and that flow, unfortunately, is not contractive anymore in Wasserstein. So that's an observation that Jan Maas and Matthias Erbar made already 10 years ago. So this flow that comes out here from this primitive discretization, that is only semi-contractive, and the semi-contractive. That's not that they cannot prove it's contractive, but they really give an example where they show there are initial data for which the trajectories diverge, and this initial this divergence is of the order inverse proportional to the spatial discretization. Yeah, so this diverges completely when the discretization goes to zero. Okay, so now what we could prove now 10 years later is when you go to the weaker metric, so from Wasserstein to diffusive transport, then the contractivity remains. Yeah? So this is somewhat surprising that that the simple discretization destroys one kind of contractivity but preserves the other. Good. Now let's go for the most probably most interesting example, which is the DLSS equation. That is the equation of fourth order, and looks like this. It's a little bit like the big brother of the heat equation, yeah. Because when you're when you would have here just one derivative, and this would be the dx log rho, so the dx rho over rho cancels the rho, yeah. And this would be the just first derivative of rho, so you would get the heat equation, yeah. If this was just one derivative, here just one derivative. But so it's a fourth order equation with quite different properties. So what you, I'm going to say about the origin of this equation in just a minute. But just for the moment, you can have a look at how this equation behaves when you feed it initially with something that is very flat, and you let the evolution run. Then then the profile develops these wobbles that are going down. These wobbles will later join into one big wobble, and only then it behaves more or less like the heat equation, in the sense that everything goes uniformly to the homogeneity. Yeah, and this is really what poses a challenge in this equation, that you do not have a minimum principle. Yeah, so what people can show is that there are non-negative solutions to this equation, but there is no comparison principle that would tell you initially you are above this level and you stay above this level. Yes, please. There's a minus. There's a fourth order equation. So in second order equation, you have a plus on the right hand side. The fourth order equation, you need a minus. Yes, if you like to, yeah. I mean, the point is that the Laplacian is a negative operator, and but the bilaplacian is a positive operator. Yeah. So this, no. Okay, so where does this equation come from? So the original derivation was by the Derrida, Leibowitz, Speer, and Spohn in 91. They were looking at interface fluctuations and the so-called two models. One of these plus minus cellular automata, yeah, and there was a region with predominantly plus spin, predominantly minus spin, and this. Look at this interface that derived this equation. There's another completely disconnected derivation that comes from the quantum moment method, and I'm going to comment on this later in the talk. And then there is a very recent derivation by Mielke, Schlichting, and Stefan, where they are deriving this from somewhere as a master equation for chemical reactions. I hope that's right to say so. Okay. Good. About the existence, so the existence started in the mid of the 90s. So first with the showing positive strong solution, but just for short times, essentially up to the first point where the solution hits zero. Yeah, so you can just use classical methods. Then later, the first big step towards proving global existence was here made by Jüngel and Pinnow, who established a weak formulation that also works beyond points of contact with zero. And then they gave the a priori estimates to go beyond these points. And 1D, that's where we generalized then later to dimensions 2 and 3. And then eventually, these three people here, they realized what is the gradient flow structure behind this equation. And then they developed completely much more advanced tools that allowed them to give global non-negative solutions even in any dimension. About uniqueness is some of the weak points here for this equation. There is some formal idea that already appears in this paper by Jüngel and Pinnow, and namely that the flow is contractive in the Hellinger distance. But that is only formal. That only works as long as the solution remains positive. As soon as the solution touches zero, which cannot be excluded, these computations that lead to contractivity, they become invalid. And then later, much later, Julian Fischer would make this formal idea rigorous, but only for a very particular class of solutions. And so one of the motivations for this entire research here was that we eventually wanted to identify class of initial or the class of solutions in which we have uniqueness, and this approximation by discretization. That shall be our main tool. About positivity, the positivity is really the thing that's bugging here. Yeah, so nobody knows if solution become instantaneously positive or not. This is essentially open. Okay. Just for so one quick illustration why this positivity issue is so closely connected to possible non-uniqueness. Yeah, so there are analytical data, yeah, finite Fisher information, finite entropy, and so on, that makes this nonlinear term on the right-hand side of the equation vanish. Yeah, so you take two more derivatives of this here, so this is clearly zero. There's a caveat, of course. Yeah, so when you compute this here, so this function has a zero. It's a 0.1/2, and this somehow is not allowed, yeah, to put in the equation. But so formally, you have this, and you could expect that it should give you a stationary solution, but it's not. Yeah? And what we are so any notion of uniqueness should somehow exclude such nice initial data from admissibility. Okay. Good. So what is so here's the spec sheet of DLSS. So for the DLSS equation, we have non-negative global solutions, and these non-negative solutions, they form a flow that is almost contractive in the Hellinger distance. As I said, so it's contractive up to the first point that you hit zero. That is fortunately non-contractive, but still gradient flow in the Wasserstein distance. So in particular, we know that the Fisher information that is a Lyapunov functional, and there is again non-contractive gradient flow in the diffusive distance for this entropy functional. So I hope that's better. So how is this all possible? What's the source of all of this? What's the source of all the structures? Essentially, you can rewrite this fourth order equation in several different forms. And also formally, everything is equivalent. Yeah. So the first form that I gave you just some slides ago, that is the one that is best adapted to seeing the gradient flow structure in this diffusive distance. Yeah, you see the dissipation of the logarithmic functional here. The next form for writing things with a square root here, that is well adapted to studying the gradient flow in Wasserstein. Yeah, so you see that the Fisher information is dissipated, and there's a last form that is well adapted to studying the contractivity in Hellinger, where you write everything in square roots. Yeah? And once you have this form here, it's really just something like a 4 or 5 line computation to show that the flow contracts in Hellinger. Concerning later than the analysis for the rigorous analysis, yeah. This rests very much on the dissipation of the entropy functional along solutions, and here you use this first form, yeah, which gives you a dissipation of this type, so as rho times the second derivative of log rho to the square. And this you need to transform into something that's actually useful for doing the analysis. And as you can see here, so a useful quantity for doing analysis is a square root. And indeed, you can dominate with this dissipation term here, this second derivative of the square root. But this is an inequality that took a while to be proven. In one dimension, it's not really a big deal, but in several dimensions, that was somehow found by several groups at different times. I mean, the proof essentially is an integration by parts, but you need to do the right integration by parts. Good. We are discretizing the DLSS equation, and essentially using the form of the square root. So what we are doing is we are rewriting the fourth order operator in the normal Laplacian and one Laplacian that Giuseppe calls the geometric one. Yeah. So you're replacing the arithmetic mean by a geometric mean of the values. And for that discretization, we can show it has an instantaneously positive global solutions. They are a contractive flow, really in contractive flow, yeah, in the Hellinger distance. It's a non-contractive flow in the Wasserstein distance, a non-contractive flow in the discretized diffusive distance. The respective functionals are discretizations of the functions that we found in the continuous setting, so discretized Fisher information, discretized entropy, and then the mobilities there, they look a bit wild, but they are nice concave functions, so we can do that. Okay. Now, why is all of this true? Essentially, because we found a form that of the equation that can be with which we can mimic all these rewritings that we already used in the continuous setting. Yeah, so we can rewrite this equation here as in such a form that is a gradient flow adapted to the diffusive distance. We can write it in this form, which is adapted to the discrete Wasserstein distance, and we can rewrite it in this form, which is adapted to showing contractivity in Hellinger. And then for the rigorous analysis, again, we are relying very much on this first form here, and we are proving the dissipation of the entropy functional, which again gives us more or less an integral of rho times the second derivative of the logarithm, and that dominates the second derivative of the square root. This again is not easy. So most of the work actually went into here. So in effect, you need to prove an elementary inequality of this type. But first, you need to see how you come from this thing that you want to prove to this elementary inequality. Okay. Oh yeah, right. And this here is another thing that I wanted to show to you. So this shows how why the flow is instantaneously positive. So we can rewrite the flow consistently in the square root form. Yeah. So here's a Laplacian of the geometric Laplacian, and then you divide everything by 2 times rho, which comes from the derivative here. And now imagine a situation like this. Your density would be 0 here, and there's one nearby step where the density is not 0. About the other values that are just here with dotted, I don't really care. By the very special form of this geometric Laplacian, which vanishes as soon as one of these 2 here vanishes, you can show that the value here at the bottom of the geometric Laplacian must be non-negative. Here it must be strictly less than 0. Here it must be less or equal to 0. And what comes out is that the value of this combination here is strictly negative. So you have something negative here in the numerator, and then you divide by something that is 0, and that means that such a state would be infinitely repelling, and that makes sure that you never run into 0. Okay, so that is by the way our big achievement. Yeah, here we compare our discretization with other discretizations in the literature. So we are looking at who is able to dissipate the entropy, the Fisher information, who is contractive in Hellinger, who has a Wasserstein gradient flow. Yeah, and then you see there's like these detergents that says that removes blood stains but does not remove alien slime or so. And this is so the only one that does everything is of course the one that that we just created. Okay, for the rigorous analysis, yeah, here's what we would like to show is the uniqueness. We cannot do that now, but at least we have an alternative proof for existence. We start with an initial datum, we discretize the initial datum, we solve the ODE, we consider piecewise constant interpolation, and then we have convergence in various spaces of this of our discretization to this form of this weak form of the DLSS equation. Okay, good. This is here's the sketch of the proof, but I think I have already shown you all the relevant ingredients. Then let me go to my to the other longer example that I wanted to show about the where a very simple discretization, ridiculously simple discretization, does a good job, and that is related to statistical mechanics, yeah, which is not really my comfort zone. So I'm probably going to tell you now everything that I know about statistical mechanics, just to introduce the model here. Yeah, that is something that I'm doing with my student Eva Maria Roth. I'll give you yet another derivation of the linear diffusion equation or heat equation, and that goes as follows. Yeah? You're looking at a probability density on phase space. Yeah? F is a probability density on phase space, and let's say you want to have the spatial density fixed. So when you integrate out the velocity coordinate, then you have then you end up with a certain spatial profile. And now among all these functions that do this, all this probability distribution, you seek the one that minimizes this relative entropy function. Yeah, so you have the F log F, and then there is a penalization of high energies, of high velocities, of P squared times F. So and you can immediately find what is the minimizer. The minimizer is a max variance, so it's rho of x times e to the minus p squared. Yeah, which I write for reasons that will be apparent become apparent on the next slide in this form here. Okay. Now you can now you use this in the following way. You're looking at the evolution of this density by just letting the particles float freely in space. Yeah? Then you look at large times. That is what this operator here does. But you force the particles also to be close to the manifold of max variance. So as you assume that there is some kind of interaction between the particles that you do not really specify further, you just say this forces the probability distribution to be close to max value. Okay, so this is what you introduce here on the right hand side, and then when you do the what people call the Chapman-Enskog expansion, what you find is that you end up with this linear diffusion. Yeah, so this density function, yeah, this marginal of the F, that satisfies this equation, which happens to be a gradient flow in Wasserstein for this entropy. Now, people do the same thing for in the quantum world. Yeah, I mean, this already the last slide was somehow very foreign to me, and now this is really tricky here. So you replace the probability distribution on phase space by an operator in L2 on the line. You replace the constraint that the spatial density is a given function rho by such a condition here on the operator. So we are looking at density operators. It's a trace class operator. So they have there's a kernel that has a well-defined diagonal in L1, and you ask this diagonal should be equal to a prescribed function rho. And then among all these density operators that do this, you minimize the relative von Neumann entropy, which is operator log operator minus the h square Laplacian r. So the Laplacian replaces this p square that I had on the previous slide. What comes out is surprisingly similar to the previous case. You get a so-called quantum Maxwellians that look like this. Is an operator exponential of something related to the density plus h square Laplacian. Well, this is very, very similar to before. So instead of e to the minus p square, you have here this Laplacian operator. Now, what's the difference here is that this logarithm. This logarithm is not just a plain pointwise logarithm, but it is highly a non-local operator. So you're turning this density. For the density, you're solving here an inverse problem, and you're trying to find the respective operator r, and then you read of this as a Lagrange multiplier. So this transformation going from rho to log rho, that is not pointwise but something local. Okay, once you swallow this, then you can do just as before. So you look at the free evolution for large times, and then you force things to this manifold of quantum Maxwellians. And then what people showed, was that you have such a Wasserstein gradient flow here of something that looks like the Boltzmann entropy, but instead of the pointwise log rho, it has this quantum logarithm in here. Okay, so everything looks very complicated. Now my student Eva came to me and said, "Why don't we discretize this?" So what I want to do is I want to replace the operators by matrices, and I want to and this constraint about on the diagonal, I want to replace it just by here the diagonal of the matrix, and then I want to do everything as de Gong and Ringhofer and so forth did. And then I said, if you listen, this is quantum mechanics, that's complicated. Such a simple approach will never work. Yeah. And then those of you who know Evie, she never listens. Yeah. So she did it, yeah, and then she found out, well, you can write down the minimizers in such a nice way. You can even rigorously go through this procedure with the Chapman-Enskog expansion, and you get a nice equation that is a discrete gradient flow of this kind. Okay, so that is what she. And then I said, okay, if you listen, so you might get out something that looks similar to the previous equation, but it will be something completely different. There will be no analytical properties that are shared by this. Well, if he never listens, and she forced me to go through the analysis, and what we found was that it's actually this thing, the flow that comes out here, that converges to the flow before. Let me just, so I skipped one slide. Let me just say a word on this. Why should this be interesting here? So the connection to to what you've seen before is this: when you expand the right-hand side of this quantum equation in terms of the quantum constant h bar, yeah, so the semi-classical expansion, then you find the heat equations, then you find this DLSS equation. They are more interesting operators that appear here. So that's so somehow things are connected. Yeah, good. And so, yeah, I'm almost out of time. So let me just tell you quickly the story how it went on. Yeah. So for this non-local quantum model, there was essentially no existence theory except for one result by Pinot, who showed that when you start sufficiently close to the to uniform distributions, then you have global solution. But you really needed this sufficiently close to stationarity, because he needs to avoid coming with rho even near zero, yeah, because then he cannot solve this inverse problem that defines the log rho anymore. Yeah. Okay, but so the good thing is, in his work, he discovered a lot of other nice properties for the equation. Namely, for instance, that the entropy, this quantum entropy, is much stronger than the usual entropy. That actually controls the H1 norm of the density. Then there is the usual dissipation estimate that even gives you a control on the first derivative of the logarithm of rho. And then this was very surprising to me. And there was even a monotonicity of this quantum logarithm. So nobody understands what the quantum logarithm does, but it's a monotone map, and that was extremely useful in the analysis. So for those of you who know more about quantum mechanics than I do, this is Klein's inequality. Yeah, at least this is a consequence of this. And now so the model that Evie cooked up, it has precisely the same properties. I didn't want to believe it. Yeah? And this is not, now these are not one-line proofs anymore. Yeah, but you really need to show something here. And it turned out you have the same dominance of the first order of the discretized H1 norm. You have this dissipation estimate, and you even have this monotonicity. And that allowed us to give now a discretization-based extension of this existence result. Yeah, what we could show is, if you go through the same procedure, it takes initial datum, discretize it, run the ODE system, define an interpolation. So this interpolated curve that converges to a weak solution of the nonlinear quantum drift diffusion equation, as long as the solution remains positive. Yeah, so we have continuity of rho star. So if initially we are positive, we know at least there is some time until first we touch zero, and on this interval of time we have the convergence of this quantum logarithm, which is mainly due to the monotonicity. Yeah. Okay, and I think that is. Oh yeah, right. So here's a generalization. Yeah, honestly, it's time for lunch.
So many thanks, Daniel. Questions?
Yeah, thanks, Daniel. Very nice. So I have a question about this quantum DLSS. So from the so a basic property of these evolutions should be when you pose them on density matrices. So these rows are density matrices. That it's operator non-negativity preserving and trace preserving. So I wonder whether this is true for the discretizations.
It is. It is. Yeah, it's one of the many things that I didn't want to believe in the beginning. But it's really so. Once you're you're brave enough and just write down everything with matrices, takes a primitive discretization of the Laplacian by the central finite differences. It's a two-line calculation. If you see, it's positivity preserving, and it is it preserves the trace. Yeah.
Thank you for the very nice talk. And then what happens when you discretize time, or which kind of properties are preserved? Are the schemes stable in time?
Actually, I think so. So for the last model, so Pinot had his proof precisely in this discretization in time. So, and the difficulty that he met was when he wanted to do the implicit time step, so he needed to make sure a priori that this that he finds a target that is strictly positive, and this imposed this condition for him that he needed to be close to equilibrium from the very beginning. I think when we are with this additional discretization in space, we don't need this anymore. So this let's say the definition of the discretized quantum logarithm, we understand much better than those guys, despite their, I don't know, 10 papers that they wrote on this about the continuous one. So we understand much better, and I think we can overcome this. But I mean, on the other hand, when we can solve it continuously in time, there's not really a need to do a time discretization anymore. But I mean, it's a philosophical question.
Thank you.
And what about the monotonicity? So you have some contraction, at least for the positive solution at the end, or?
Yeah. So we see. So first of all, we are hoping very much by this analogy here that even this weird quantum equation is contractive in Hellinger, but we at the moment we are far from knowing how to approach this. This inequality here, is actually better than stated. So here we can control some distance between the Maxwellians. And this can be exploited, but we are still far from understanding this really.
So if we don't have other questions, so we can thank Daniel again. Just wanted to make two short announcements. So for lunch, just arrived at the same restaurant as usual. Lunch should be for registered people, which means almost everybody, but I think there is no problem with the number of people that we are, so you're all welcome to come for lunch. And the other announcement is that there is a small change in the schedule that you can already find on the website. So there is an exchange between the time slot of the talk by Jan Maas and Franka Hoffman. So Franka will speak on Friday and Jan will speak tomorrow. But it's already updated on the website. And we resume at 2:30. Okay, welcome back, everybody. So today, the afternoon session will start with a talk given by Elsa Cazel from the CNRS and the University of Toulouse. And she will speak about principal component analysis in the pseudo-Riemannian Western space. Thank you.
Thank you very much. And thank you for having me. It's okay or? No, okay, perfect. So yes, today I will talk about principal component analysis, PCA, a way of summarize the mode of variation of a data set in the space, in the Wasserstein space. So basically what we will have in here, and I will present several ways of doing this. So basically what we have is we have a population of probability measure, mu1, mu_n, and we want to summarize the mode of variation of this data set along some objects. So I will do a quick review of how to do that in the Hilbert space, and we'll then go through probability measures. So in the classical Hilbert space, we have points, x1, xn, so or vectors that are in here that are presented in R2. And we want to find a line, okay, that goes through the mean point and that will minimize the distance of the point to the line. So this is exactly what is written in here. We look for a vector in the Hilbert space H. We normalize it, and we want to minimize the distance of the projection between each point and the projection of the point on the line. Okay, so this is classic PCA. We have seen that in statistics a long time ago. And now what we want to find is the second principal component in this case, where we want to find another line that will be orthogonal to the first one and that will minimize the projection, again, of the points onto this line. Okay, so this is classical PCA in Hilbert space. What we want to do in this talk is that now each point will be a probability measure. So now what is a mean point? What is a line? What is orthogonality in this kind of spaces? Okay. So some example, why do we want to do that? Okay, so in here, I have absolutely continuous probability measures that are just Gaussians with random mean and random variances. And if we consider this density probability function as function in L2 of R, which is an Hilbert space, we can actually apply directly the tools of the machine learning tool or statistical tools of an Hilbert space and do PCA, principal component analysis, in this space. So in this case, this is what we will obtain. So in here, in black, I represented the Euclidean mean in L2 of R. Okay, so the Euclidean mean, it's nice. It's also a probability density function. But when we do the PCA in this space, we will obtain this kind of figure. So what does it mean? In here, I have computed mu1, that is the solution of the previous problem, where H is the L2R space. Computationally speaking, it's really easy because doing something in the continuous space in here, it's quite equivalent when we do computationally to taking each of these density measures as a vector. This is between minus 200 and 200. So we can represent it within a vector, okay, discretize the probability density function, and then just apply a classical PCA. And that we will obtain the first mode of variation U1, and T represents the projection of each of my probability density function onto this line mu1 with direction mu1 that go through the mean point. Okay, so T is basically the scalar product in my L2 Hilbert space of each of the measure with mu1. Okay, so in here, what I present, the lines in blue represent just this this curve with different T. Okay, and each T represents the projection of one of my data point that are the Gaussian distribution function. So what's going on in here is that when we do that, obviously, as we can see in here, we completely lose the structure of the probability density function. So we have something that can be negative, and of course that doesn't sum up to 1. Okay, so it's not a proper way of doing it because we lose completely the Gaussian information in this kind of summary. Yes. So this is T with minus 0.3, and this is T with 2. Yes, exactly. And so it's just because also in L2 you can extend the line as long as you want. Okay. Now this is just the second mode of variation, and you can see also that we have the same problem of not being able to understand the meaning, how to interpret this kind of mode of variation. Okay, so it's really as in the R2 setting, or here a line. This time, sorry, each point is a probability density function, and then a projection on this line is also a probability distribution function. Well, it's sorry, a curve in L2. Okay. So this is why it was interesting to develop actually a PCA in the Wasserstein space, meaning that we want to stay in this space in order to have meaningful modes of variation of our dataset. So, okay, this one, you all know that. Just maybe we will write a map in here that go from mu to nu as this T, okay? An optimal map in the sense of Monge. So now we want to use the Wasserstein metric in order to analyze our dataset. Okay, so obviously one of the main issues is that the Wasserstein space has curvature as long as we are in dimension higher than 2. Okay, so all the flat space Hilberts, all the flat structure of an Hilbert space cannot be used that way. And also, it's not a Hilbert space, of course, but it is a geodesic space with a pseudo-Riemannian structure. So we will help ourselves with this kind of result in order to develop a proper way of doing PCA. Yes, exactly. We have a tangent space and okay, so here are several ways of doing it. So this is a review. So first of all, we can consider one-dimensional distribution. So in this one, it's easy because actually for one-dimensional distribution, it's kind of a flat space. Well, it is a flat space when we look at the quantile function. In here, we will work only with absolutely continuous priority density function. Another way of doing it is solving an approximation of the problem with generalized geodesic. I won't talk about this one, but we can talk about it later. Another way of doing it is linearizing the Wasserstein space. So for that, I thank Cathy and Quentin, because with these two talks, it's really easy to understand how to do that. But I will go on explaining what are the differences between linearizing and just looking directly at the object in the geodesic setting. Then we can do PCA in Riemannian manifold and just inspire ourselves with this kind of method in order to develop the same kind of PCA in the Wasserstein space. And at the end, I will present the PCA in a quotient space that is that has been developed by Ekman, Otz, and Monk, and we are interested in this result in order to extend it in the Wasserstein space with the autogeometry. And this is ongoing work. Okay, so in this talk, I will just talk about these three way of doing it and present it and present these three PCA-like analysis into a Wasserstein space. So the one-dimensional case. So as I said before, in here we have the classical PCA into the Hilbert space, where we look for a line, a vector in the Hilbert space with the distance of the Hilbert space. And we are looking for the set. So the SU is just, well, U is the direction and SU is the line given by this direction, okay? And so in order to solve this, we want to decline all of these ingredients into the Wasserstein setting. So naturally, the vector mean will become the barycenter, so the Freshe mean with respect to the Wasserstein distance. Lines will become geodesics, and the orthogonality will become orthogonalities in tangent space. So the last one is not very natural, but it's kind of the only way that we found it in the one-dimensional case in order to ensure orthogonality of the measure. Because what does it mean to be orthogonal in the Wasserstein space? Okay, so this is this definition from Biko and his co-author, where we have in here the first principal component analysis. So in here, you recognize exactly the same setting as the Hilbert space, just we have replaced the distance squared by the W2 distance squared between mu I and gamma, which is a geodesic passing through mu and bar. And mu and bar is the barycenter in here, as defined by Guillaume and Martial Aguet in their paper. Okay? So it's exactly the same setting. We are just replacing what we know to exist in Hilbert spaces with objects from Wasserstein spaces, okay? So I just recall in here, I just put like the geodesic between this Gaussian and this Gaussian, and the barycenter in the one in the middle. So these are really known results, okay? So when doing, how do we solve this? Now that we have this setting, so I recall that in here we will do the analysis in the one-dimensional space. So in here we can rewrite everything in the one-dimensional. Yes. A geodesic with a starting point and end point. Yes, because otherwise you cannot extend it. I agree. So, so what we will do in practice is that we will find a starting point and an end point. Before that, I can use this exponential map and logarithmic map that are given for a one-dimensional measure for at a point rho that is absolutely continuous on the compact set omega in R. So the exponential map is defined as the push forward of the identity plus the curve in L2. Okay, and the logarithm map is defined as the this composition of quantile function and cumulative distribution function minus the identity. I recall that we are in R, so everything is quite easy. Okay, so once we have this, we have this nice result from also Bigot and co-authors that are actually, when we restrict ourselves to this set, meaning the set of curves that can be written as a log map, basically, we have an isometry between two measure mu1 and mu2, and the log map of this measure with respect to the L2 metric weighted by rho. Okay, so once this parallel is done, when this isometry is done between these two quantity, it will be natural to work directly onto this log map in order to apply a PCA. Because in this case, the PCA in W2 will be equivalent to the PCA of the log map in L2 of rho. Okay. So in here, what I'm looking for is that now that I have the setting this isometry, I want to find a line in the Wasserstein space. So in line will become a geodesic. Robert interpolation. And what we have in here is that if we take 2 points nu0 and nu1, maybe I can write in here, in W2, and if I take a line in L2 of rho, okay, mu, sorry, I wrote it mu in here. Okay, so we will have actually the equality of this line, which is a geodesic in L2, and this geodesic in W2 thanks to this equation. Okay, meaning that what I'm going in here is that I have nu0 and nu1. I map them into v mu of omega by the log map. Okay, and obtain 2 points in the flat space, the Hilbert space that is flat. A line in this place, a line in this space is really a line. Okay, so I draw a line, 1 minus t w0 plus t w1, where these are the log map. And then when I go back to the Wasserstein space through the exponential map, I will actually obtain the geodesic. Okay, so everything is nicely done, and we will see that if we restrict ourselves to this space, actually we can do the step go and forth and just work like that to obtain a principal component in the Wasserstein space. Okay, letting that sink in. Up. So the thing is, this space, okay, defined as the log map. So actually, you have to find to choose a base point at each time. But this space of log map, it is not linear, but it is closed and convex in L2. So this will allow us to use a proximal algorithm in order to find the principal component analysis. So this is how we have done it. So I'm going really quickly on that, but in here, since we saw that finding a geodesic in the Wasserstein space is equivalent to finding a line that is restricted to the space V in the L2 space, I'm just looking for a line, so span mu, within this space V, such that the projection of the log map, my W E, and I want to minimize the distance to this point. Okay, so it's exactly as I have done before. So I have points which are log maps, and I'm looking for this one to minimize the projection to this line, but by staying into V of mu n bar. Okay, because I have chosen the barycenter in order to flatten my space in this point. Okay. So this is exactly what I wrote in here. So we want to stay in this space in order to stay in the W2 space. Okay. So when we have that the line mu1 star and all of these projections are staying in this space, actually just doing the PCA of the log data log data is just equivalent to doing the PCA of the log data constrained to remain in this set. Okay, meaning that the only difference is that all the projections are in the set, in the convex set. So the question is, so when we did this proposition, so we are a little bit annoyed because we have to do this kind of projection, and which is just a little bit more involved computationally. So the question was, is it really necessary to do all this step? Maybe we can just look at the log map. So the log map is equivalently what is behind the linearized optimal transport. But is it not enough to look at the log data, the log map, sorry, and doing a PCA in this space, okay, without the constraint of having the isometry? So I will try to answer to this question in this next section. So just some results. When we do the PCA, as I've showed you before, we will obtain something like that. So in here, we have obtained mu tilde 1, okay, with the propositions that I've shown you before. And we represent the geodesic that we have embedded thanks to the exponential map to the Wasserstein space. Okay. And so what's nice is that we recover with this first geodesic. Again, the first one represents for t equal minus 70, and the last one for t equal to 81. So what's nice in here is that we recover all the variation in mean of our data set. Okay, and with the second one, we recover the variation in variance of our data set. And why is it this separated in this case? It's because I have chosen actually, so this is not, so I have chosen the points. So this is the half plan of mean and standard deviation, okay? And I've chosen the point following a uniform distribution, so that observation of a uniform distribution, the mean and the variance, in this way. So of course, the first mode of variation, if you think in a L2 way, not in a L2 way, in a R2 way, will be this one, and the second one will be this one, okay? So we will see the variation along the mean and then the variation along the standard deviation, okay? So this is really because of how I have chosen my Gaussian distribution. Okay, so with this example, I hope that you are convinced that it can be interesting. I mean, if you result, yes, no problem. So it can just, okay. So now another way of doing that. So still, it's the same idea behind this, is that we want to obtain we want to take into account the geometry of the Wasserstein space in order to do statistical PCA. Can go on? Yeah. Okay. Oh, sorry. Thanks. So linearization of the Wasserstein space. So Cathy talked about this, Quentin talked about this, and basically what we are doing in here is that from this paper of Wang and co-author, the linearized OT is defined as the distance between the transport maps. Okay, so what's happening in here is that we choose a biased point. In here, I will call it rho. Again, everything is absolutely continuous in this setting. And we will find the map that send rho onto mu1 and the map that send rho onto mu2. And then instead of looking at the distance between mu1 and mu2, you'd look at the L2 distance weighted by rho between the maps, the optimal transport maps. Okay. So of course, once you have, so these are all things presented by Cathy and Quentin. So when you have this Mange map, you can embed the U measure into the linear space L2, and you can do all of your favorite statistical tools, statistical analysis into this nice Hilbert space, okay? So in here, so classically for PCA, you will perform a PCA on these maps. So to recall, in the 1D case, it is exactly what we have done. But in the 1D case, the thing is we have the isometry that we lose in here. Okay, but it's exactly the same way of doing so. And then I can just show a quick application from my PhD student Erel Gachon that applied this linearization of OT to represent a data set of flow cytometry measurement into a 2D plan. Okay, so flow cytometry measurement is that it's a patient that go through that has leukemia and that go through chemotherapy, and so we have a measurement of his cells. So these cells are around 10 to the power 5 cells, and they are in dimension usually 15 or even 17, okay? So in order to represent this patient in the 2D space, sorry, we can apply a PCA in these maps. So what she did actually is that in order to, when you have these kind of maps, you have to choose a reference measure. In here, we have chosen just the Gaussian with covariance their identity, but you have to compute all of these maps. Okay, so in order to compute maps that are in a less that are in dimension smaller, in order to not have all of these points, what we have done is that first we did a k-means on the merged data, which is just the classical mean of the data. And then we have computed nu I on the quantification of mu I into nu I, where we have fixed the same support point, and we just arrange the weights in order to be close to the measure. And then we embed them, and then we do PCA in the map. So in here is just a small example of how it can be. It can help just by separating the different source of variation of a data set. Okay, so in here we have 7 laboratories that are all of these markers. And we have, for each laboratories, a patient. We have 3 patients, and 3 patients go through the same measurement into these laboratories. Okay, and what we can see is that with the linearization of these maps of this discrete measure, we can obtain a really good separation of the patient into these labs. Okay, so this is just so this work was with the hospital of Bordeaux, and it was in order to help them to see what kind of patient will have a problem and what kind of patient they should look into, because it's kind of different from the other distribution of patients. Okay, so this is just a small application of PCA in linearized OT. And now I just wanted to open the question of, so as I showed you before, I wanted to do an exact PCA. The question is it necessary to do an exact PCA actually? Because what we can do is just use the tangent space as some priority row, compute the map, and these maps, maybe it's enough to just look at this map in order to do meaningful PCA. So in here, for Gaussian, it definitely is. So for Gaussian, the fact that when you flatten them through the Mange map, actually, you will find that this is good enough to obtain the variability of your dataset, meaning that the PCA on these maps is already pretty convincing, and we don't need some more information about the geometry, the curved geometry of the Wasserstein space for the Gaussian distribution. What do I mean by further distribution? It is not clear. So there is one of these results from Cantor, where we see that actually we have the equivalence between the W2 distance and the L2 distance at rho between, so this is mu and nu. And so we have already this equivalence, meaning that, I'm repeating myself, but doing a PCA on these maps seems kind of equivalent of doing this PCA on directly the Wasserstein space somehow. Actually, when we look at this really simple example, so in here we have two probability distribution. In orange, it's mu1, in green, it's mu2, and in here, it's rho. So it's my base reference distribution, okay? So this is a uniform on the square. What's happening is that when we apply a geodesic in the W2 sense, you will obtain that this rectangle will change into this rectangle and this one into this one, okay? It's quite nice. But what we obtain if you do in the L2 row sense, you will obtain some moving of the mass that is not wanted, okay? So in here, what does it mean geodesic in the L2 row sense? It means that we have computed these maps, okay, from rho to mu0 and from rho to mu1. And then we have computed in the Hilbert space L2 of rho the geodesic, so the line between these two. And I would see that there is a mixing of the mass in here that is unwanted. Of course, in here, I'm cheating a little bit because I've chosen an example where it will come up to that. But if in here I had chosen not the uniform distribution, but for example, the barycenter of the two, we would not have obtained this, but we will have end up with this exactly. Okay. What I mean is that if in this simple example I can crash the moving of the mass, I can crash the way of I want the mass to move. In much harder example where I don't have two distribution, but I have a bunch of distribution and I want to find the variation, might be that this won't be satisfying. Okay, so this is why we have thought about using PCA in a quotient space, and this is ongoing work with Alice Lebrigand, Nina Vesseron, and Thierry Klump. And so in here, we want to leverage the autogeometry in order to do PCA through the flat space again, but not defined in the same way. So in here, very briefly, for the Gaussian case, okay? So in here, I identify the space of Gaussian, the centered Gaussian distribution with a space of SD plus matrices, okay, symmetric definite positive matrices. And I choose a reference point, the identity, which correspond to the Gaussian with mean 0 and the covariance identity, okay? And what can I do is that I can define the top space, which is the space of general linear matrices. And for each covariance matrices in here, I can look at the fiber on top of this covariance. Okay. So what I have here is a fiber that is defined thanks to this application pi that at each matrix in GLD send A transpose. Okay, so why it's nice, I will show why it's nice, but basically what we do is that if you are in this fiber, okay, through the application pi, you will end up on sigma, on this one. Okay, and what's nice is that in here, in the top space, I have actually the inner product, which is just a Frobenius product, the inner product. Okay, and this is because I have chosen rho as the identity, rho as a Gaussian with covariance identities that I can write this, but otherwise I will have just another inner product in here, weighted inner product. And what's nice with this geometry is that, so yes, that's a fiber. Again, so the fiber is defined as all of the matrices that are projecting onto sigma. And this can be rewritten just actually with one representer of the fiber. So this is just the square root of sigma and the space of orthogonal matrices. Okay, and thanks to this fiber, I just can move into this fiber, okay? What's nice in here is that at each point in here, okay, at each point, we can decompose the tangent space with direct sum of vertical and horizontal space, okay? And for Gaussian distribution, all of this is known, and all of this is closed form. So now I'm going back to my problem of PCA. So again, the problem of PCA is finding a direction. So in here, direction is still a geodesic. And what we want to do is that using this nice property that if we have at any point GLD, and we are at the point GLD, and we're choosing a direction that is in the horizontal space at A1, we will have an horizontal geodesic. What is called an horizontal geodesic. And why is it nice? It's nice because actually an horizontal geodesic is projected onto a geodesic in the Wasserstein space. Okay, and in here, you have this equality also that when you look for the distance between two covariance matrices in the bottom space, meaning that you're looking for a geodesic, it's just you have to look at the 2 points in the two fibers such that I'll align well in order to match the infimum of this distance and match the geodesic distance. Okay, so now that we have all of these ingredients, we want to apply to do a PCA actually in this space. Really, it follows. It's a little bit harder, but it follows the idea of flattening everything and to work on some things that we know how to work with. So now, how does it work? We have covariance matrices, okay, and we want to solve this problem where we have the nth on the geodesic, such that we want to minimize the distance between the projection of sigma I onto this geodesic. Okay. So one way of doing this is that rewriting the problem directly on the top space with the inner product that is the Frobenius inner product, and by finding a line on which I project each of my representative of the fiber, the right one, okay? So I move on to the fiber, and I want to find the line that will always minimize the distance between the line and the fiber. So in here, I'm hiding something again. Maybe I can write it in here. So in here, it's the same. In the same spirit as before, we cannot extend geodesic at infinity. Actually, in here, when you choose a line in GLD, at some point you will cross a hole. By a hole, I mean a matrix with determinant 0. Because T, if you take T, going to infinity and minus infinity, at some point you will cross a hole. So what's happening when you cross the hole is, it's quite funny, is that you arrive at the hole, so as in a geodesic way, and then you go back, but not on the same geodesic, on the another geodesic. So you have to take this into account when you do your computation. And so this is a little bit mistaken, this figure, because in here it seems like GLD is some kind convex, which is not, obviously. Okay. Okay. So in here, I have a really quick example where I have only 5 Gaussian distributions in 2D with a representation in the plane. And what we will obtain is the first component will have the variation in the rotation, kind of. And the second component will have the rotation into the eigenvalue. So this is kind of disappointing in any case, because when you do tangent PCA with Gaussian distribution, you will obtain exactly the same thing. It's really, really close, which makes me think that actually I would like your intuition on this, but the Gaussian space is kind of flat. I'm not going to say that, but it seems that it's not really curved when we're looking at this kind of PCA. Okay, and that what I've presented with Gaussian, we can extend it into for the space of priority distribution supported on compact omega, including RD. Okay, so it's the same principle. It's just that everything will be harder and more involved. But basically, what we have is that you have the bottom space, which is the space of priority distribution. you choose a reference measure, okay? And you look at the fiber into, in the top space, the fiber that is related to rho, okay? And same, if you choose mu, you look at the fiber that is defined, again, with this application pi. This time, this application will go from the differential diffeomorphism, sorry, that go from the diffeomorphism, the top space to the bottom space, the probability, and that is defined by the push forward of your reference measure rho. Okay? And so once you have all of this, you can define the fiber as all of the diffeomorphism, such that when the push forward of this diffeomorphism with rho is equal to mu. And again, this, I don't know if you written it. So this can be written in a way of just considering one representative of the fiber, and then all of the measure preserving diffeomorphism of our reference measure rho. Okay, so the take-home message with this kind of with this kind of geometry is just that we want to recover a flat space in order to do easier computation. In this space also, we have that the tangent space decomposes into a direct sum of vertical and horizontal spaces. Okay. Okay, so I won't go into more details on this because it's still complicated. And at the end, for the spoiler, we will, for this, we wanted to solve this as a variational problem, and it was kind of difficult. So now we are just looking with neural networks if we can solve this problem by just parametrizing the objects with the neural networks. Okay, because these vertical and horizontal spaces can be written as gradient of function and composition of function, and this is how to do it. Okay, so what are we looking at next? So we are looking obviously with this problem with the autogeometry. And this is a very important problem also, how to deal with discrete distributions. So all of what I've presented in here, everything was with absolutely continuous distribution. So now what do we want to do? If we want to do the sort of tangent space, we can always find the optimal plan and then choose a barycentric projection, for example, of this optimal plan, and use these maps as the maps for the linearized optimal transport. But all of these are kind of approximation on approximation on approximation, and we don't know how to really present it as a discrete problem for probability measure, discrete probability measure. And also, so this is another ongoing work with Clément Bonnet, who thought about performing PCA, as in this paper from Chamy and co-authors for hyperbolic spaces, where instead of looking the projection onto the line of the probability measure or just the mean of the distance, to look at the Boltzmann function. So yesterday we saw the Boltzmann function, which is kind of a projection, and it is exactly the same idea in here, using, instead of the projection, the Boltzmann function. So the idea is to minimize the variance of the Boltzmann function, and and you will end up with another way of doing PCA. The question is, are all of these way of doing PCA equivalent? We have seen that the tangent PCA, so using linearized map, is not equivalent to doing true PCA. But what about this other way of doing it? It's quite unknown. Okay, thanks for listening.
So many thanks. Do you have questions? So I start with one. So I could be wrong, but I thought that the PCA was one of the main goals of the PCA was to have an increasing sequence of vector spaces with dimension which increases, where you can project and see most of the peculiar information. But here I the impression that the focus is not, so you never obtain a two-dimensional vector space. You obtain two orthogonal lines.
Yes.
So there is not a way to define a manifold in the set of measures, which is the important one on which to project. I guess for Gaussians, it could be done. But
actually, yeah. So actually, the iterative way of doing it, so finding the first one and the second one and so on.
Then when you have two lines, do they span something? That's
you can always, well, choosing a representation and with those two lines is also a problem. So how do you represent them in this space? But what we did in one dimension, we tried to recover a two-dimensional space into which we project this probability distribution, and it was less interesting in terms of results, less let's say discriminating the probability distribution than when we do iterative way. But I'm not sure why actually. Just that the variation were not that explicit. But of course, this could be a more natural way of doing it, but it's also more complicated.
And not easy to interpret, as from what you say. Some other questions? Otherwise, we take a few minutes break and we thank our speaker again. Okay, ready to go on with the second talk of the afternoon. So it's a pleasure to introduce the talk by Anastasia Rajvoronska from Université Claude Bernard in Lyon. And she will speak about the fully discrete JKO scheme, both for nonlinear diffusion and crowd motion. Thank you, Anastasia.
Thank you for the introduction and for the kind invitation. Indeed, I'm going to introduce what we call the fully discrete JKO scheme. So fully discrete stands for the fact that we want to discretize the JKO scheme in space. So in spirit, it will be some similarities maybe with Daniel's talk. First, we want to discretize in space, and somehow we want to do it in the simplest way that is relevant for that problem. But in general, yes, it's part of the effort with Filippo to get to know everything about the JKO scheme. So, of course, the starting point for this talk is a standard JKO scheme or minimizing movement. As you all know, I'm just trying to fix the notation. So I'm going to work on compact set omega, which is a subset of RD, and given some time discretization parameter, we run this iterative scheme where we minimize energy plus Wasserstein distance. And we all know that that's the way to approximate solution to the like big class of equations that have gradient law structure in the space of probability measure. In this talk, I will focus on this type of energy. So I usually have some nonlinear diffusion and external potential. And examples we're interested in is, of course, Fokker-Planck equation, like the basic example of an equation that fits in this framework. Then we want to cover porous media equation, where the energy is some power law. Of course, it would be also nice to talk about fast diffusion equation with this polar, with the exponent m is smaller than 1, but this we're not able to cover at the moment. And there'll be one more example that's a bit more special in some sense. So it comes from this crowd motion model. You can see it as a limit of the previous equation, like porous media equation, as you send exponent m to infinity. So instead of some power, we are getting like a really new variable pressure, which relates to the density in this specific way. And you can also see that this energy that corresponds to this model is also like you can obtain as a limit as I'm going to infinity of the previous energy. So just maybe I will give a bit more explain a bit more about this model because this maybe it's not that well known. So the idea is like you want to model a movement of the crowd or some group of people. So this group of people just follows like the advection equation with some restrictions. So they want to realize some preferred velocity, and because we were with gradient flow structure, we need to restrict to the case where your preferred velocity is a gradient of some potential. But we have a congestion constraint or like concentration constraint. So people, the density cannot concentrate too much. So to like mazes, like precise definition of this model. We do it through duality, so we introduce the space of this pressure variable, the dual variable, that makes sure like exactly that you only allow velocities that will not lead to concentration of the measure, so your densities always stay below 1. And compared to this, we have like nice compact formulation in the as a approximation as a GQ scheme, where just we add this constraint and have the potential energy in there. So that's examples we're interested in. And in principle, why we want to discretize in space, because we have some goal maybe to use it for some numerical schemes. In principle, there is like, at least it's theoretically appealing to use GQ scheme for developing numerical schemes, because, okay, it already gives you nice discretization in time. You will know that you will preserve some structural properties, and it gives you some stability. And it was already quite some schemes that were based on the GQ scheme. And of course, the difficulty when you discretize is how you deal with the Wasserstein distance, because it's a minimization problem in itself, so it's not that easy to discretize. And a lot of like computational like tools and tricks that developed for Wasserstein distance, you can also try to apply for the GQ scheme. And mainly, probably the most successful class of the schemes is based on the Benamou-Brenier or dynamical formulation of the Wasserstein distance. So there is this augmented Lagrangian approach, which, and later it was like primal dual also methods, a bit like improved methods based on the same idea. And also, like in Benamou-Brenier formulation, you know that you have some integral in time. So to minimize it, you will need to do some inner stepping. But so it's like every step you also need to do some minimization problem. But in practice, usually you don't need that many steps, so it kind of works. But another approach also based on Benamou-Brenier formulation that actually wanted to avoid this inner stepping. It's based on some kind of linearization of a Wasserstein distance that, okay, for closed measures, you know that Wasserstein distance is almost like h-1 norm. You can use it. And another approach is like maybe based on Synchron algorithm. So when you add entropic regularization to your Wasserstein distance, and there is approach which is also based on semi-discrete optimal transport, where you also have some specific discretization of the Monch-Ampere equation. So that's like very short, not complete overview of what was already done for the GQ scheme. And somehow what we do is simpler than everything that was done before. So the idea is like, okay, we want to discretize this space. Let's restrict our measures to a regular grid. So our formulation of the fully discrete GQ scheme basically says, okay, let's restrict minimization to the atomic measures that live on like this vertices of this regular lattice. That's it. And we still use the standard Wasserstein distance in there. It's kind of important because there is there's this general idea in gradient flows that as soon as you go discrete, you shouldn't use Wasserstein distance. It was a big effort to like give gradient structure to the diffusion equation on like graphs or discrete spaces. So it goes to work on Jan Mas and Alexander Milke, who really introduced the appropriate transport codes that would give gradient structure for discrete diffusion equation. And yeah, in that situation, it's really necessary because if you restrict to the graph and you try to use Wasserstein distance, you will not have geodesics in your space, so things fall apart. But here, we somehow make Wasserstein distance work in some sense, because we cheat a bit. It's like not like fully discrete problem, because on each step, like time step of your GQ scheme, you restrict to the lattice, to the discrete measures. But when we reconstruct the curve, we're still allowed to do geodesic interpolation in between these time steps. Because we're still using full domain omega, so like in between these time steps, you kind of allow your measures to leave the lattice and follow the usual geodesics. So that's why it works. And yeah, so here you also put inside the discrete energy, which is like natural discretization of the energy that I showed you on the first slide, where we also see that somehow it's just like natural for this problem. So to discretize this inner energy, it's kind of you think of your discrete measures as a piecewise constant on the squares. And yeah, okay, for potential, you can just still think about as a sum of direct deltas. Somehow, this using both ways to kind of embed discrete measures to continuous space as a sum of direct deltas and as a piecewise constant density is like a really useful trick that helps to prove some convergence result. But yeah, so that's our fully discrete GQ scheme. And the task we give ourselves, and like what I want to show you a bit in this talk, is to prove convergence of this scheme in the joint limit as your space and time discretization parameters goes to 0. Yeah, so convergence to the solution of the equation that you expect. And again, a slight detour about like, okay, so here we want to prove convergence, but we also have some application to numerical schemes in mind. It's especially natural for this crowd motion case, because now if you look at this problem, it's basically like linear minimization problem with a linear constraint. So you have to use some linear programming tools. So there is some hope that it might be efficient. We restrict to the regular lattice, so where there is some special algorithms that allow you also to calculate this Wasserstein distance in a faster way, just because in the regular lattice you can treat your geodesics like in the systematic way. You can reduce the number of connecting paths that you consider. And another hope is that we would be able to use some displacement bound, some nice bound, infinity bounds of this type. So these types of some bounds on this quantity are known in continuous settings for the Fokker-Planck equation. So it's basically something of order tau. And it's also, at least there is some bound known for the crowd motion case, where like it will be of order tau to some exponent. So far it's not known in discrete, but it might help implement the numerical scheme, maybe prescribe these restrictions. So we'll be able to compute the Wasserstein distance faster. And yeah, about like really convergence result, that's what we have for the nonlinear diffusion. I'm just like repeating the formulation. So yes, of course, convergence result, we're able to do exactly what you expect, converge to the solution of this equation. And under some assumptions, of course. So in the case when we don't have external potential, you can consider just basically any convex superlinear F. And as soon as we add potential, things are getting a bit more complicated. So we need to So F just convex is not enough, so we introduce something that we call quantifiably lyrically convex, which basically would mean that you need some lower bound on the second derivative of F when it goes to infinity. It's nothing crazy, and I will specify probably later. So, but for solutions, I mean, you just have. Okay, so here I'm talking about convergence of solutions, right? So you reconstruct this probability measure, like the curve in your space. So it converges like uniformly in tau and Wasserstein distance, and you have, yes. Yeah. It's very similar to also what happens for standard Wasserstein distance. Like basically it's sorry, it's very similar to what's happened to standard GQ scheme. So basically it's formulated like the same way as you would formulate convergence of standard GQ to the solutions. But it will be more details later, so I think it will be more clear. So actually one restriction that pops up in this theorem is that we need some relation between space and time discretization parameters. So we require this h over tau goes to 0. So people who know numerical methods can recognize it as reverse CFL condition. And in principle, again, for numerical point of view, it's probably not the best because it means that you need to discretize in space much finer than in your time space. So it's okay. But it's very easy to see that this one, we really need this relation. So it's not like a technical problem. So you could see it already just if you consider the movement under of particles under the external potential. No diffusion here. So basically all your particles move independently on the grid under this potential. So basically GQ scheme to reduce it. So like for each particle, you're looking for the next location that minimizes this functional. So it's like natural discretization to corresponding ODE. And the condition that ensures that your x1 is just different from x0, because the minimum distance you have to travel is h on a lattice, like just to move. You see that h over tau has to be smaller than this Lipschitz constant, just to ensure that you move, that you're not frozen. And in principle, you can calculate in this situation, at least for linear potential, like exact arrow. So it's really h over tau pops up in there. So it's essential for convergence. So compactness is never a problem in this problem. But to converge to solution, you need this relation. If like your h over tau is bigger than this Lipschitz constant, you're frozen, you don't move. And if it's of order, like of the same order, h over tau, you can move, but your discretization, depending on like some angles, can introduce some additional drift into your limit equation. So you converge to something, but not the solution. So I want to show you some ideas of the proof, how we prove this result. And of course, it's very much based on the like classical proof for the standard GQ scheme. And I just want to show some interesting things like that doesn't work in discrete setting exactly as a continuous, and how you find some replacement. So the idea, the strategy of the proof, you want to go for the one step of GQ scheme to the sum energy dissipation identity. Yeah, so from GQ, you want to first maybe find some discrete analog of this energy dissipation identity that will allow you to nicely pass to the limit and recover the solution of the limit equation. So here I'm introducing notation for the Fisher information that pops up here. So it will be like important object, so it will be quite important to understand how to get the Fisher information. And the like first step, how you get from the GQO to some inequalities that already look a bit like energy dissipation inequality, is based on the variational interpolation or like the Georgi interpolation. And this is known, and it's in the Green Book, and this translates to the discrete settings without changes. So like from one step of GQO, you obtain this kind of inequality where here is like this special variational interpolant that you put inside. So this you know how to do. Then what you usually like typically do in continuous settings, you want to like bring your Fisher information or your slope somehow, right? That's what you need in the continuous. So in principle, in metric spaces, there is a slope estimate. So you know in general metric spaces, it's the distance between these two consequent steps of the GQ scheme and bounded from below for some local slope of the corresponding energy. And it's very nice, but that will not allow us to pass to the limit. So this local slope, something that really doesn't work in these discrete settings. And so that's why in blue, I just put the inspiration from continuous settings, but yeah, we need to find some replacement for this slope estimate adequate for our discrete situation. And so how we do it in discrete? So we have this lemma where like it does similar job, right? So you have a lower bound of the consequent step of your GQO scheme by some discrete version of the Fisher information. And again, as you see, so this h over tau like terms pop up everywhere. So if to be able to pass to the limit, you need this h over tau goes to 0, but as we already expected. And the discrete formulation of the Fisher information that we need is like very natural, like finite difference kind of discretization of the continuous Fisher information that I showed you. So assuming that you have that, so you found like this is discrete replacement for your slope estimate, you just plug in it to your current version of energy dissipation inequality. And then you need to do compactness and convergence results. So that I think that was the question about the what kind of convergence. So this convergence of the curves is we are getting it in the same way as for standard Wasserstein distance. So here the tools from continuous translate very nicely to discrete. So to get the lim inf inequality for the Fisher information, we need like strong compactness of this like thing that goes into discrete Fisher information. And to get this type of compactness, there is a lot of tools like available, like from numerical scheme, finite volume numerical schemes. There's also like known tools how you can get it. And yeah, with this with proper reconstruction from discrete to continuous, you can get the lim inf inequality for the Fisher information. Which yeah, so here you're basically done. So combining this all like compactness results and this convergence, so this energy dissipation thing nicely passes to the limit, and you recover the energy dissipation formulation for your limit equation, as you expect. And another detail of the proof that I wanted to show you is idea in this lemma 1. So in this slope estimate, right, when you bound your Wasserstein distance between consequent maximizers of the GQ scheme with the Fisher information. So again, what works nicely and continuous in discrete, you can write down optimality condition for one step of the GQ scheme, where like you're getting like Kontorovich potential here. And what you can do in continuous, it's like quite immediate. So you can write down your Wasserstein distance in this form using the Kontorovich potential, then optimality condition, like the continuous one, where you can differentiate, gives you equality of gradient of the Kontorovich potential with the gradient of this, and you just obtain your Fisher information. So that's inspiration for continuous. On discrete grid, you cannot differentiate. So you need, and also this is not like, also there is not formulation of a Wasserstein distance like that. So in discrete, we find something like a discrete integration by part, kind of this. And here we use a lot like monotonicity of f prime. So that's why, so basically like just obtaining this inequality is crucial to get this slope estimate in continuous. And also here, that's why if you just have nonlinear diffusion without external potential, this inequality is easy to obtain by monotonicity. And when you add external potential, so there is also some difference of potentials here. The idea is like your potential can destroy monotonicity, but that's why we require this a stronger like quantifiable convexity assumption. So we make sure that our F is convex enough to compensate for whatever potential can do, because potential is Lipschitz. And that's where this idea where the assumptions that you saw in the formulation of the theorem come from. And I think just want to show you, we're also able to prove similar result for the crowd motion case, where the strategy is the same, but okay. Of course, you have nothing like quantifiable like convexity anymore. So, so we would need to require a bit more from potential. So we really need C1 potential, but then also just by carefully doing like computation and using the special form of the pressure, which like relates to your density in very specific way, you're able to make the same strategy work and recover also convergence result for the crowd motion model. So that's just a summary of what I presented. So that's a fully discrete GQ scheme that I showed you. We have the convergence result in these two cases. So the natural continuation for this project is also implement this numerical scheme. And also the interesting question, if we can find some useful displacement bound in discrete. If so the idea is like in the continuous settings, the displacement bounds are obtained using the Monch-Ampere equation. And this is something that we don't know yet, like how to do in discrete or what would be discrete analog to Monch-Ampere equation and the strategy of the proof. So if somebody has some intuition, like how to do like discrete Monch-Ampere, I would be very interested to discuss. But with that, I just want to thank you for your attention.
So thank you, Anastasia. Questions?
So you mentioned that one of your ideas that you had for implementing it numerically was some good ways of computing W2 between empirical measures on a uniform grid. Do you mind saying a bit? Did I understand correctly?
I mentioned that there is some like algorithm. Oh. I mean, like when I get just reference to okay, so you can a bit reduce the computational cost of Wasserstein distance on the gradient on the regular grid, just because like think about like 2D, any like your connecting curves like easily decomposable into like horizontal and vertical part. So and you don't need to consider all like possible like connecting curves. You can do just between 2 points. You can always just consider one that first goes horizontally and then vertically. And then this allows them to reformulate computation of Wasserstein 2 of this minimal cost flow problem. And yeah, it gives a bit reduction in the cost. Yeah, I'm not sure if I can give you more details now, but yeah,
thank you.
Okay.
Thank you. So what actually depends on the fact that it's a grid? Could you replace it by any other dance or something?
Like you mean replacing like HZD with something more?
Yes. What do you need? What do you use of it?
The problematic, like the bottleneck, is actually the slope estimate. Somehow we need to reconstruct for the slope estimate. We need to reconstruct gradient somewhere exactly, and it's easy to do on the regular grid because it's always like, okay, your gradient has these two components, and I don't know in the moment how to replace, how to do it on more general graphs. Actually, everything else would work for like more general grids, but this one is a bit tricky.
Yeah, so I wanted to ask briefly about the assumptions for the crowd motion model. You said that the function v in that case has to be C1. So you do not assume anything on the, that it's Lipschitz, you do not assume that the gradient is bounded, or do you?
I mean, I'm working on a compact domain.
But
so it's something like C1 up to the boundary.
yeah, sure, but okay. So maybe I saw wrong that it was RT.
It's a bit confusing. I'm writing like C1 on the full space, and then I work on a compact domain.
Okay.
Sorry, that's probably
okay.
caused some confusion.
Okay, that's clear. But okay, but I also wanted to understand then why the extra regularity comes into play. If it's easy to explain. The continuity of the gradient.
Easy. Do I have some? I think somewhere like in fish information, you need to do lim.inf, and you have a product of like something like discrete gradient of your potential times your density. And somehow you do some Wickstrom convergence, and I'm only able to do it with C1 like potential. So I need some continuity for gradient, and then I have like something Wick convergence on the other side. It's somewhere in computation.
Okay, thanks.
Short question, which came from Enrico's question about the kind of convergence that you have. So far the answer is we prove weak convergence of the measures. Do you think that if you take your atomic measure on the grid and you replace it with piecewise constant densities, like spreading the mass of each atom on each cube, maybe this converges strongly L2, strongly LP? Should, no?
Sure, strongly, probably density in L1. Because we have strong convergence for these functions L of your densities. So I think from there you can improve basically to the strong convergence of this piecewise constant densities.
I can continue on the topic, why then thinking of using finite element instead of finite difference? Finite element instead of using essentially finite difference. Using other discretization scheme, especially like.
Sorry. That's the simplest, right?
Yeah, but
I promise. Let's do discretize in the simplest way. I think you're probably right.
So you did not consider. You started with that, and it's really already difficult.
But what would be the benefit? I don't know if it works in like
it's
inference. It is very intuitive and it gives you the result.
Yeah, but you get also the anisotropy of using the grid, while you have more freedom if you use finite element.
Yeah.
It might be an option that you can consider.
Yes. Okay, that makes sense. Yeah.
Yes. Thank you very much for the very nice talk. So, just by curiosity, is there a connection with the work of Sandier and Serfati about convergence of gradient flows, and when you have a metric space and you approximate it in some way, and there are conditions on slopes and so on, and the kind of proof you presented, there's some similarities. Does it have the? Can you elaborate on the comparison between the two, or it's not so obvious?
It has the same spirit, right? You have this class of proofs that's called like evolutionary gamma convergence, or like an EDP convergence for the gradient flows. I feel it, it's probably like similar strategy, a bit similar strategy. I think in Sandier Serfati that they require a bit like more, right? There's this convergence of the slope. But it's a bit like variation of the similar approach, I would say. Just, I think when you want to adapt it to discrete, that's the way you do it, like with just gamma convergence of the Fisher information instead of some convergence of slope, I think.
Okay, so I think we will stop here and thank Anastasia again. So we're ready for the last session of the afternoon with two talks. So the first of these two talks will be given by Davide Carazzato from Scuola Normale Superiore, and he will present a maximization problem for a Wasserstein type energy.
Thank you, Filippo, for the introduction and for the invitation. First, I apologize for the title that is not very informative, I realize, especially for this conference and for this audience. But I didn't find any proper name for the function that I will talk about, so you'll see the definition in a couple of slides. This talk is based on a joint work in collaboration with Almut Burkhard and Ihsan Topaloğlu, and stemmed from another say minimization problem that is a shape optimization problem. So my talk will be divided in 3 parts. The first one concerns the introduction of this energy and its how it is embedded in another problem, in a shape optimization problem. So why it is natural, at least it was natural for us to look at the maximizers of this energy. And then I will address that problem, first understanding the existence and then characterizing the maximizers that turn out to be balls through a symmetrization procedure in this case. Okay, so let me fix the framework that is the Euclidean space with cost that is the p power of the distance with p strictly larger than 1. And okay, as you all know, there is existence and uniqueness of the optimal transport map when we work with densities in Rn. And in dimension 1, it will be important to know that we have existence, uniqueness, and also an explicit description of the transport map. That is the monotone rearrangement of the densities. So very explicit, and this is useful to see work by hands at a certain point where where otherwise we don't know precisely what to do. So what about the energy that we were interested in? That energy is defined fixing a power strictly larger than 1, and for any density in Rn, which takes values in 0, 1, an L1 density, we define the transport energy for that density as the minimum p Wasserstein distance between that density and any other function v that is non-negative with the same L1 norm, so we can compute the transport distance, and that satisfy this compatibility condition. That is, the sum of the two functions of the two densities has to be smaller than 1. If you want to think about some examples, let's start with the characteristic functions of sets, and this functional, the transport functional applied to that density, in a sense measures how much it is expensive to move the mass from that set into its complement. And in fact, if you think about it in these terms, you can think about this problem as a partial optimal transport between as a partial optimal transport problem between the density u that is given and the density 1 minus u that I hope you can see, it is here, with the mass parameter that is given by the L1 norm of the density u itself. If you're not familiar with the partial optimal transport problem, you simply have two measures or densities, and you want to transport a certain amount of mass that is fixed, in this case the L1 norm of the density, but it is not assigned which part of your densities is moving. So it is up to you to choose which one, say, part of the density it is more convenient to move. Okay, but by the way, this is not really important for this talk, but it's nice to know that it is a framework that has already been studied in the literature. So first of all, let me do a little bit of heuristics about this functional. For example, let us take a set A, and well, if you want to do some calculus of variations, maybe you want to compute some variations of this energy, so we try to move some mass from the set A to somewhere else. If you move it far away, you poke a little hole in the set and you move the mass at large enough distance, then you see something that doesn't really speak with the new set A tilde. You have a non-local problem that is in some way a finite range, that is a finite range interaction in some way. Second, we define the energy for densities, and for some of them the functional is trivial. In fact, suppose you have either the density that is completely smaller than 1/2 everywhere, or just in some region that is isolated from everything else, then you can leave the mass where it is, right? Because you have enough space. For this problem, to compute the transport energy, we have existence and uniqueness, in the sense that for any density u, there exists a unique pair of a companion density eta u and the optimal transport map tu that satisfy this chain of equalities. That is, you can compute the transport cost for your density u, exactly as the distance between you and another given density, one given density. And another property that is a more geometric property of this functional is the so-called inner ball condition. That is a property actually of the companion density, in the sense that if you have your density u, and the point x is transported somewhere by your map tu, then you have a ball where you completely saturate the constraint. Like eta u completely saturates the constraint in this blue ball. And it is very easy to understand why, because if you had some space to put some mass, like in here, you could move the mass at shorter distance. Okay, so you are not doing something smart, moving the point x so far away. This will be important later, but it is a very, very simple geometric information that is easy to understand already. So why do we care about this functional? Well, it has been studied, this sort of energy that is an isoperimetric problem, if you like to call it that way, to represent some biological membranes. And people were interested, of course, in trying to find minimizers for this energy. And you realize that the transport term is in competition with the perimeter, in the sense that if you take a set and you slice it in very thin stripes, for example, you are decreasing the transport term, because you can, creating this space in the middle, you allow to move the mass very little. So you are decreasing the transport energy. Of course, the perimeter instead is not very happy when you do something like that. So the two are in competition. And this is basically why we started to study the maximization of the transport term. In a sense, if you try to minimize, you understand that there are no minimizers among sets. Among densities, there are many, and they are sort of trivial. And we wanted to understand how this competition between the perimeter and the transport term goes on. And one way to understand that is to try to study the maximizers of the problem. And this kind of energy, the perimeter plus the transport term, is was studied in some papers. Among them, you find a short list here. Some of them, like the first two, we are more focused on the applications, so really on the biological models and the mathematics, of course, but they were more interested in that. Some others study like either this functional or like the transport functional or some close relatives of it. And some others, like I didn't tell all the story about the functional perimeter plus transport term, but there were like generalization concerning the transport cost that one studies in that in that functionals. And finally, I mentioned the last paper that appeared essentially at the same times as ours on arXiv, where they address the same problem, the same maximization problem. And let me say that the results are stronger in the sense that they allow for more general transport cost, but the techniques are very different, very different. In fact, they introduce, they work with the dual problem, essentially, and they introduce the Kantorovich potentials and they work with them. Instead, our approach is completely, is very geometric and works like directly on the primal problem, as you will see. And like to me, it is more like closer to my intuition what's happening when you work with the primal problem. But okay, I understand it is probably my limitation to struggle with the other way. Okay, so let me now address this the maximization problem. So first of all, the existence of maximizers for the transport energy. And well, let me fix a bit of notation, let me define the class of admissible densities that are nothing else than the L1 densities with a given norm and that are bounded by 1. And first of all, you can prove that the functional T, the transport cost, is continuous in the class AM with respect to the weak star convergence. And to clarify what I mean by this sentence, well, this means that if you have a sequence of densities in AM that converge weak star to another density in AM, so there's no loss of mass, then you have that the transport costs converge. And this may be not terribly surprising, because it is like the transport cost is defined in terms of the Wasserstein distance that induces the weak star convergence, the weak star topology. Okay, and something like you should like care about the moments of your densities. In theory, in practice, not really, because you can prove a priori a pointwise bound on the transport distance for this problem. Okay, just to say, it is not really an issue, the fact that you should be a bit careful. Once you have continuity, you can prove directly the existence of maximizers by sort of standard tools, that is using the concentration compactness principle. That is, you apply that principle to a maximizing sequence of densities, and you realize, okay, if you exclude vanishing and dichotomy, you remain with compactness that is enough, since you have continuity. Okay, if you believe me that there's continuity, there's no problem after that. So you want to exclude vanishing, and that is like it is not difficult to see with using this geometric information, that the inner ball condition, that when you see vanishing, your energy is going to 0. So it is not a maximizing sequence. Okay. Instead, when you want to exclude the second case, the dichotomy case, you look at the scaling of your energy, and you realize that it is superlinear. So since your dichotomy means that you have some mass that stays say bounded, and some other mass that is going at infinity, and since your energy has a finite range of interaction, sort of, you can see that they are really decoupling. So you see that it is not convenient to decouple if you have this scaling. It was convenient to stay bounded. And then these two things exclude vanishing and dichotomy, and so you realize you have existence. And then we can actually characterize maximizers. And to do that, I anticipated we argue through a symmetrization procedure. And our strategy is divided in 3 steps. Basically, the symmetrization procedure is done in the first step, that is the most important one, and it amounts to proving that when you have a maximizing density, then its associated transport map to compute the transport cost is radial with respect to some point. Radial and with, sort of a positive coefficient. Radial means that each point is mapped along one ray and the center is fixed. And once you have that, you have a lot of rigidity. You can expect to use it very, very efficiently. And actually, I mentioned that we had to we work in one dimension. That is precisely the case. If you know that the transport map is radial, you basically reduce your problem to a transport problem along each ray. Okay. So you look at the maximizers in one dimension for this problem, and you can prove essentially by hands that segments are maximizers, are the unique maximizers of this energy in 1D. And this means that your density was a generic density a priori. Actually, you can prove that it necessarily is, say, a segment along each ray. So, in other words, you are like, if you have a maximizer, then it is the characteristic function of a star-shaped set. After that, you do one last step that is actually incredibly simple, that if I have time in the end, I will briefly sketch what we have to do. And that uses this geometric information that is encoded by the inner ball condition. So I will now concentrate on the first step, that is like the most geometric one, and where you see the symmetrization procedure. So first of all, let me start in general, when you try to do symmetrization, for example, for the isoperimetric problem, you want to start from any set. So let me start from any density, U, with a given mass that you can think to be fixed as 1. And let me take an hyperplane, H, that divides the mass in equal parts. Okay. Then you look, say, at one side, like at the left side, and you symmetrize it by reflection. Okay. So you end up with something like the yellow region here. Now you try to compute the transport map associated to that density. You realize easily that the transport map is actually symmetric by reflection again. And since it is symmetric, you can, suppose now you find a point X that is mapped through the transport map across the hyperplane H, the hyperplane of symmetry. And since the transport map is symmetric, you find another point on the other side that does the same thing. But this is clearly not optimal, because you could do something like that. Okay. So in particular, the important information in this picture is that the transport map associated to a symmetric density doesn't cross the hyperplane of symmetry. Okay. Then let us start with let us use this information to produce a candidate transport map for any density. And this consists of gluing the two maps that we constructed before. In the sense that if you have a density, you can symmetrize one side, the left side, compute the transport map, and put it on the left of you, because that map doesn't cross the hyperplane. And you do the same on the right side. So you end up with a candidate that estimates the energy of U. In the end, you obtain this inequality, computing the cost of this gluing. That is, the transport cost to the power P of a density is smaller than the average of the two symmetrizations. Okay, so far so good. We work with any density, but we know that a maximizer exists, actually. So we work with a maximizer, U. And you look at this inequality and you realize, okay, if U is a maximizer, then also the two symmetrizations are maximizers. And moreover, so they are maximizers, so you have equality. Now the uniqueness pays out, because if you have equality, you know equality is obtained exactly gluing the transport maps. So you know that the transport map for the density for your maximizer is precisely the gluing. Okay, and the important information that you should get out of this is that the transport map doesn't cross the hyperplane that you chose that splits the mass in equal parts. Now you iterate this procedure and you obtain an n-symmetric density that is symmetric with respect to n orthogonal hyperplanes that I call U bar, and that is still a maximizer because you proceeded like symmetrizing, and we said that after symmetrization you remain a maximizer. So you end up with something like that. And now to conclude that the map is radial, you should simply realize that what you did before worked for any hyperplane that splits the mass in equal parts. And if your density is n-symmetric, any hyperplane that passes through the origin splits the mass in equal parts. Okay? So in the sense, TU bar doesn't cross any hyperplane that passes through the origin. This might already convince you that the map is radial. Otherwise, you look at these pictures that might maybe convince you a little more. That is, say you take one hyperplane and you say that is invariant, that is mapping to itself by TU bar, and the same goes for another hyperplane, any other hyperplane. You combine this information, you obtain that this cone is mapped into itself. The hyperplanes were arbitrary, so you end up with a radial map for TU bar. I think I have some time. Okay. So the second step is works by is done by hands. It is not very enlightening, say, but it is not particularly hard. And the final step that actually took a while to realize that it was not terribly hard consists in proving that if you have a maximizer that is star-shaped, then it is a ball, actually. So let me start from a maximizer that is the yellow blob that is star-shaped. Okay, it is so its boundary is parameterized by a map that is this phi, and that is simply a multiple of the point on the sphere that you are using to parameterize your set. And when you actually work on the problem, on the one-dimensional problem, it is possible to see that the transport map computed at the point on the boundary of this set simply maps the point into a multiple, a constant multiple of itself. Okay, this 2 to the 1 over n. So now the conclusion follows applying once more the inner ball condition, and that shows that the map H, that is the parameterization of the boundary of your set, is 2 older on the sphere. 2 older on the sphere means older with exponent 2, so it means constant. And actually, you see, again, this is just a few pictures, but if you write down this thing, is just a 2D geometry, very simple. You have a point here, h omega times omega, that is mapped up there, and another point on the boundary of your set that is mapped somewhere else. And you write down, or you draw your inner ball condition, that is, you depict one ball, and that was saying that in this ball, the companion density saturates the constraint. If it saturates the constraint, you know that this point lies outside of that pole. Okay? Because this red point is on the boundary of, is on the boundary of this red blob that is actually just a descaling. Okay, so you swap the roles and you get another condition. And once you combine these two things, simply writing down what these two inequalities mean, you obtain your desired inequality, the two-holder inequality. So the map was constant. Okay, I think I'm done, and I thank you for your attention.
Questions?
So P greater than 1 was needed just to exclude the dichotomy case?
No, okay. The dichotomy case actually works works actually also for P equal 1, but like we wrote down our argument thinking about the Wasserstein distance because it is superlinear in any case. But it doesn't really require that form of the cost. P equal 1 is used in a more in a crucial way to say that you necessarily don't cross any hyperplane that splits the mass in equal parts, because you can always run the symmetrization procedure obtaining a maximizer that is n-symmetric, whose transfer map is n-symmetric, but then we don't really know how to do this step, like saying that when you take any hyperplane, the optimal transfer map, one optimal transfer map doesn't cross the hyperplane. I mean, you can find one, but it is it is not known if for any hyperplane you could find a different map a priori. But let me also be more precise, because I told you that there were like this other work. There was this other work that considers more general cost that also considers the case P equal 1. So the result is true in any case.
Yeah. Have you considered also the problem with other upper bound, not just one, but some function, maybe possessing some symmetries and so on, so it makes sense to say something about properties of maximizers?
Okay, not... see, there are works where they consider functions of this type we didn't consider for the maximization problem. So it was considered in the literature, something like that, but not for the maximization. Okay, not by us, for sure. But you're thinking maybe if your bound is symmetric, you expect a maximizer that is symmetric.
For example, yeah, symmetric in some sense, yeah, with some group or some extra.
Seems very reasonable. Yes, in fact, yeah.
Thank you.
So maybe it's contained in the argument when you use when you got the 2 to the power 1 over n. Do you have a general fact that if you have a transport map of the form lambda of x times x, then lambda is constant? For instance, for p equals 2, the fact that the function of the form lambda of x times x is a gradient should put some constraint. Because I don't exactly see, and you can see that then the boundary is transported to a constant factor, but
I mean,
I didn't get the argument.
Well, it has to be a maximizer, I think. Otherwise, I'm not sure. I mean, you can always maybe I didn't understand properly the question.
It's true that if you know that the optimal transport map
Yes.
is of the form scalar lambda of x times x,
Yes.
then automatically lambda is constant. I don't know if it is true, but
for
p equals 2, for instance, for simplicity.
Okay.
If it is the case, then you immediately get the fact that the set is sent to a scaled version of it. And then with your two older argument, you get the fact that it's a ball.
I mean, if you know that it is a priori a multiple of the point, like you basically reduce to the rays working on each ray, right?
Okay, so you decompose the problem on each radius.
Yes.
Okay.
But it has to be a maximizer, otherwise. It is, say, a scalar multiple and full stop.
And full stop. Does it imply that if you want this to be a gradient, this gives some condition, no? Grad lambda should be directed as x, so lambda is a radial function.
Well,
no, yeah. So lambda is constant is false, for instance, because lambda, but lambda could be radial, which is probably enough to obtain that you sent.
I mean, if you start from any density, you could take this density.
Mm-hmm.
There, lambda will not be constant.
Okay.
Okay. So.
Okay.
Yeah. It is still radial in any case, of course.
Other questions? Otherwise, we thank David again. Okay, the last talk of the day, Flavien Léger from INRIA Paris will give a talk about minimizing movement with general cost and non-negative cross curvature in infinite dimension. Thanks, Flavien.
Okay, thank you, Filippo. Thank you for the invitation. The last talk of today. So yeah, I want to talk about the sound is okay. I can hear some echo on mine, but okay. I want to talk about two recent and related projects. One is about minimizing movements, which are not necessarily based on square distance, but more general cost function. And another one is a synthetic condition of non-negative cross curvature that is helpful to prove convergence rates of the minimizing movement scheme. Okay, so I will start with an implicit. So I want to show you two types of minimizing movement schemes, an implicit one and an explicit one. So I will start with an implicit one. Okay, and my setting is fairly general. X and Y are two arbitrary sets, and I take an arbitrary cost function. And I have in mind a situation where I want to do optimization on infinite dimensional spaces. So here X could be a space of measures, for instance, and C could be a transport cost, it could be a relative entropy, and so on. And I have an energy that I want to minimize, this G here. Okay, and so this is the generalized minimizing movement that uses C as a as a movement limiter. Okay, so the form that we are probably all used to is when C is given by a square distance, for instance, a squared Euclidean norm, or a squared Riemannian distance, or a squared like metric distance on the metric space. Okay, but here I just for now assume that it's an arbitrary cost function. And I also have two lines here because I want to keep the possibility that that C is defined on two distinct spaces, X and Y. And so once I did an X update here, I need a way to map back into Y space. And so this is the role of the second line here. So here I assume that my cost is non-negative. I try to make the minimal assumption I can have. So my cost is non-negative, and I have this condition here that says that essentially the value of C here will be 0. So this is just kind of the bridge between X and Y space. Okay. Of course, you can think of the case where capital X is capital Y, and C is, let's say, a non-negative function that vanishes on the diagonal, in which case yn plus 1 will just be xn, and you will just have one line as usual. Okay? So this is called, I mean, with the square distance, this is sometimes called proximal point method in optimization. We had an earlier talk that presented the JKO scheme, so that would be the case when C is the squared Wasserstein distance. Okay. And what I want to show you is to identify a kind of non-smooth geometry that's only based on the cos C that gives me, so a convexity for which convexity of the, sorry, a geometry for which convexity of the energy gives me rates of convergence. So convergence plus rates. So we can have in mind a situation where when we're in the Euclidean case, so C is a squared Euclidean distance, then convexity of G will give us convergence rates. These convergence rates are either sublinear when you just have plain convexity, or exponential when you have strong convexity. If you are on a Riemannian manifold that is non-positively curved, then convexity of G along geodesics will give the same rates. And when you're on a Riemannian manifold that is non-negatively curved, so non-negative sectional curvature, then it's convexity of G along different types of curves, C segments, that will give you a rates of convergence. Okay, and so the question is, what can we say in this case? Okay, so when we don't have smoothness, C is not necessarily differentiable. In fact, we might be in infinite dimensional spaces, and also C, there's no distance, so up here there's no geodesics, etc. Okay, and also I call this implicit scheme. This is the standard nomenclature in optimization, because if you were to actually implement this, let's say in real life on a computer, you would need to iterate this type of steps, and each step is itself an optimization problem, okay? So you need to solve an inner optimization problem, so it's implicit, okay? Okay, now I want to show you a similar, or like same flavor, explicit minimizing movement scheme. So it goes as follows. Now I assume that the energy I want to minimize is F, and I assume that is C concave, which means exactly what is written here. Here is a C transform. So it means that my energy is, excuse me, is a lower envelope of profile based on the cost function. This is what I draw here. This is my energy F. And you see that for each Y, the cost gives me a whole, I hope you can see in the back, the cost gives me a whole family. For each Y, you have a majorizing function. So for each Y, this dotted line represents one majorizing function that I called phi here. Phi is C plus FC. So it's a function of X and Y. And so you get this. And when it's F is inconcave, it means that it's a lower envelope of this family. So you can recover it from this family. And now my explicit scheme is given by this guy. Okay? So let me try to explain what this does using the little picture here. So first, given a current iterate xn in the physical space, like the space that we care, because f is dependent on x, the first step is going to select one element in that family among all the elements that are like kind of like above f, the one that is here in the solid line that minimizes the value of xn. So it's the one that touches f at xn. Okay, so this is a majorized step because you select in this kind of like a 1D smooth picture the one surrogate function that is tangent to your energy, to your objective function. Okay, so this is the Y step. The X step is easier to understand. The X step just minimizes the profile that you've just found. Okay, and then it gives you the xn plus 1. Okay. Okay, and I claim that this is an explicit scheme. Okay, so far it doesn't look very explicit because not only you need to solve an inner problem, but that quantity involves FC, which is itself another optimization problem. Okay, so even though I said I'm interested in infinite dimensional situation, let's look at what happens, because it's already interesting, in a finite dimensional and differentiable setting. So now I will assume that X and Y are smooth finite dimensional manifolds, that my cost is differentiable, and that my objective, that my energy is differentiable. And C concave, always C concave for the explicit scheme. Okay. In that case, and under additional assumptions, then that explicit scheme that I just showed you can be written like this. So this is the Y update step, and then this is the X update step. Okay, and this already looks much more like an explicit scheme if you assume or if you accept that we're able to invert that operator nabla xc, okay, which we assume is the case. Okay, then the first line will give you y plus 1 in terms of the gradient of f at, or the differential of f at xn. Okay, so this already looks also like much more like a gradient descent type of method. Okay, and like before, since I want to keep the spaces x and y separate, this gives me a y point, and so then I need a way to map back into x, and so this is the role of the second equation. Okay, the first equation can be written, so I mean the inverse of this nabla x operator is called also the C exponential map. Okay, so the first line says that y plus 1 is the C exponential map of minus nabla f. Okay. Okay. And what is interesting is that when you look at simple cost functions, you recover many of the gradient descent variants that are used in optimization. So the simplest case is here, you're on a Euclidean space, or even on a Hilbert space in infinite dimension, but let's just keep a bit simpler. You have a step size tau, a strictly positive number. If you like rewrite this scheme, you get exactly this, which is the standard constant step size gradient descent method on Euclidean spaces. Okay. This one? Okay, so this is in the little dots here. I assume that this has a unique solution in xn plus 1. So it needs to have only a unique critical point, and that critical point is the global minimizer. Yeah. In fact, in all these examples that I showed, x is equal to y, so xn is yn. So Euclidean case. Now let's look at the case of a Riemannian manifold, a Riemannian square distance on a Riemannian manifold. Then I said earlier that this essentially gives you the C exponential map. Well, in the Riemannian case, this is just a normal exponential map. In fact, C exponential map is named after the exponential map. And so what you get is the Riemannian gradient descent, which is the natural generalization of gradient descent on a Riemannian manifold done in an intrinsic way, where you now shoot along geodesics along minus along the steepest descent. Okay, so it's already nice, in fact, that you can unify these two schemes like this. And also, if you remember the previous slide, written in terms of C transform, and we're going to come back to that. But now I want to look at cases where my movement limiter is not based on a distance. So now I'm looking at a case where I'm on a finite dimensional vector space, but I don't have access to an inner product. I don't have access to a Euclidean norm. And so I cannot do really gradient descent because now my gradient is not of the same type of my iterate. Now this is a covector and this is a vector. Okay. And so what people have done in optimization to remedy this, they suppose that they have access to a strictly convex potential U, and they look at this scheme, which is called mirror descent, which was introduced in the 80s by Nemirovsky and Yudin. And so this is used a lot in optimization, especially on discrete probability measures, and U is the entropy function. Okay. And you can recover this scheme by taking as a cost this object here, which is called the Bregman divergence of the convex function U. Okay. And when you take the reverse Bregman divergence, so here it looks like the same object just with x and y reversed, then you get, I hope you can see in the back, then you get this method here, which is called natural gradient descent. So it's a type of gradient descent where you use the Hessian view as a kind of a metric. Okay. And then you get Newton's method if U is equal to F. Okay. And in fact, I mean, since this is not really an optimization type of a workshop, I won't talk about this, but with the technique that I'm going to present today, I can obtain global convergence rates for Newton, which were not known until now. Okay. Newton is known to converge very fast if you initialize close to the minimizer, but it was not known, or like general conditions on the function were not known to have convergence no matter where you initialize your method. Okay, and so this slide was to show, like one of the points of this slide is to show that this is in fact an explicit method. And in fact, if you want to do an explicit method on an infinite dimensional space, even like on a metric space, it's not so clear how to do it. And this provides, so this, which is equivalent, right, in the finite dimensional space, but this is, this makes sense on the no regularity at all. This is only spaces and C transform a cost function. This is one way to do an explicit scheme on the infinite dimensional space. Okay, and the key property is C concavity. Okay, and a last thing to note is that this is formulated as an alternating minimization of the function C plus FC. Okay, so here I update I minimize in Y, and here I minimize in X, and I didn't write the plus FC because it's a constant, but you could also write it. Okay. And so both the implicit and explicit scheme can be written as alternating minimization. So for the implicit case, it's the alternating minimization of G plus C. Okay. It looks a little bit forced to write it as alternating minimization in that case, because you're like, okay, but it is indeed an alternating minimization, and also in this case. And so if you're trying to now study convergence rates and build some theory, then you might as well just directly study general alternating minimization methods, which is what I will do here. And when I'm talking about alternating minimization, I mean this method, okay? You just have one iterate fix, you minimize the other variable, and so on. And the nice thing about alternating minimization is that it also has no structure on it, right? You can define it on any kind of sets with any kind of function. There's no step sizes, there's no gradient, etc. Okay, you just minimize, 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 minimize. You know that you decrease at every step. You just need to assume, of course, that the arguments are non-empty. Okay, but you know that you minimize at every step, but you don't know that you will converge to the infimum of phi if phi is bounded from below, let's say. Okay. All right, and so now I want to give you EVI, a discrete EVI for general alternating minimization method, which is given like this. To make it more friendly, I wrote it by splitting phi into f plus d, where f is the marginal function like this here. So in the implicit scheme, f will be g. In the explicit scheme, f will be small f. Okay, so f is really the energy that you're trying to minimize, and d is the rest. Okay, the difference. Because when you write like this, then the EVI looks familiar. It looks similar to the EVI for gradient flow that you find in the Ambrosio Gili Savary textbook. And in fact, I call it more a 5-point property because this is the name that was given to something very similar in the 80s by Cesar and Tusnadi, who were also studying alternating minimization. So what we did is we kind of remodernized it a little bit and added a strong convexity parameter. So it depends on the, like for the normal AVI, like, sorry, for the like a metric space AVI, it depends on the parameter mu. Okay. Okay, and it looks like this. And we like here in this context, the reason we care about DVI is that in some sense it's the simplest inequality that involves the iterate at time n and n plus 1, so that when you just sum over it, it gives you rates of convergence. Okay, this is just immediate. Okay, in some sense the EVI is almost the rates of convergence, but before you just sum inequalities and you get telescoping sum. Okay, so in the case where the parameter is 0, you get what is sometimes called, it's not maybe a very good name, but it's called sublinear rates of convergence. So in 1 over n, and this is true for any x xn's are the iterates, y0 is the initial point. This is true for any x, but it's often just used for the global minimizer. You assume that you have a global minimizer f, x star, so you use that x star. And when mu is strictly positive, you get exponential rates, which is in the same flavor. Okay? And I assume that, so this is in a work that I did recently. And we assume that this is the end of the story, like that's all we care about. If we have this, we're happy. Okay? So if we have this, we're happy. This is implied by the EVI. So if we have the EVI, we're happy. Of course, the EVI is, I'm just going to put it back here. The EVI is an inequality that is non-local. And so in general, it's very hard to prove directly. Okay? You need to show that this is true for any x along your iterate. And in general, it's very hard to prove directly. So the goal is to find more tractable conditions to obtain this EVI, because once you have the EVI, then you have rates of convergence, and then you're happy. Okay? And here I'm talking about kind of discrete EVI. I'm not studying here the case where you're trying to approximate the gradient flow, and so then you have a small parameter tag that you will send to 0. I only stay at the discrete level. In some sense, I'm just doing like a discrete in-time optimization. Okay? Okay. Oh yeah, and so this is the why we care about EVI, and I want to give you the final theorem that contains words that are not defined yet that I will define in the second part, but just to show you how to answer the equations that I initially asked. Okay, so how to get EVI from convexity along certain paths. Okay, and so this is the theorem. If you can find between every iterates, so x0 or an iterate xn and an arbitrary x, a variational C segment, that's the special path that I will define later. That depends on the function that you're doing alternative minimization on. If you can find such a variational C segment on which your function is convex or strongly convex in this sense, and then if you have a little bit of regularity here, then you have the EVI. Okay? So I need to explain later what is this special segment. Okay, this is just convexity of your function. That's good. That's what you wanted. And this little regularity here, of course, we need something more because our setting so far is almost too general, right? This is actually true for arbitrary sets and arbitrary functions. Okay, so you need something that says, and the path here is an arbitrary path. There's no continuity involved a priori. Of course, in practice, then you will work on spatial measures, for instance, and then you will have some continuity, etc. Okay, and so this is something that says that essentially that that movement limiter D is differentiable at s equals 0, something like this. Okay, but it's actually something not very strong. Okay, and I don't insist too much on this one now. Okay, and so now I want to let me just look at the time. Oh, that's okay. Okay, great. Okay, thanks. Now I want to explain what I mean by variational C segments. Okay. I want to talk now about cross curvature, non-negative cross curvature, and so I will just give a one slide introduction. So the story starts in a finite dimensional and smooth setting, and the story starts in 2005 when Matt, Rudinger, and Wang were studying the regularity of optimal transport, with the cost function C. C is now a 4-time differentiable cost function. And they identified 4 tensor, which is this guy here, S, and a related condition that is now called sometimes MTW condition or A3. And there's also several variants of this condition. So here I just wrote one that requires the non-negativity of the MTW tensor on orthogonal pairs of vectors. Okay. And this quantity, this MTW tensor, which depends on 4 derivatives of the cost function, was a little bit mysterious. And then later on, Kim and Macan, they showed that this quantity was in fact very natural because it was nothing else than the curvature, the standard Riemann curvature, in a pseudo-Riemannian framework that developed. And the pseudo-Riemannian metric is given by the cross derivatives of the cost function. Okay, so they made everything more geometric and more natural, maybe. And also, they looked at a stronger condition than the MTW condition that they called non-negative cross curvature, because they called the antidilute tensor, they called it cross curvature. And it looks like this. So it requires the MTW tensor to be non-negative for all pairs of vectors and not orthogonal vectors only. Okay. And they studied several properties of this condition. In particular, they proved the following characterization of non-negative cross curvature. So to state it, I need to say that a C segment is a path X on the X space with a base point Y that satisfies this condition. Okay, so it's in some sense a segment in the standard sense, but in the cotangent space at Y bar. And okay, yeah, and they showed that non-negative cross curvature is equivalent under certain assumptions, in particular C convexity of the domain, to the convexity of this difference of costs. Okay, and if we want to hope to have, or like if we're interested in a synthetic condition of non-negative cross curvature that will make sense in infinite dimension, this seems like a great place to start because we talk about convex function, which makes sense, in general. The only thing that might look tricky at first is that you need to define C segments, and C segments have a derivative of the cost. Okay? But in fact, it turns out that this condition not only characterizes non-negative cross curvature, but it also characterizes C segments. So the only way for a path like this to satisfy this condition is if it's a C segment. So you don't need to say that this has to be a C segment. You can say it has to be true for some path. Okay, and so then it naturally leads to a definition of a C segment that we call a variational C segment under no regularity assumption. So, general sets and general cost function. You say that your variational C segment if you satisfy this inequality here. Okay, so in fact, you don't actually need convexity of the difference of costs, but you only need this kind of below the chord type of property. Okay. So this is a very demanding property in general. So of course, if you give me arbitrary cost function or arbitrary sets, there might not exist many variational C segments or not at all. If you can always find variational C segments between points, then you said that you have a space with non-negative cross curvature and an SCC space for sure. Okay. Okay. And so then we studied a little bit. So this is work with Gabriele Todeschi and François-Xavier Viala. And we extended or found analogs of properties that were shown by Kim McCann, and also they were with Figali in finite dimension. And we showed that they were true in infinite dimension. So in particular, NNCC spaces are stable by products. So this allows you to build big spaces from small ones, products of domains. NNC spaces are stable by a certain type of projections, which generalize Riemannian submersion to the infinite dimension. An example of which is what was mentioned before, getting the Wasserstein space as kind of from the space of math where you forget the where you allow for relabeling. So this connects to properties proven by Kim and McCann. It's a synthetic notion that is stable on the Gromov-Hausdorff convergence, which is good for any type of synthetic notion. The metric case is also very interesting. So if you are on the metric space and you look at the squared metric as your cost, then an NNCC space is always positively curved in the sense of Alexandrov. And so this generalizes, is an analog of a result of Loper, who proved something similar, but in finite dimension on Riemannian manifolds. And we also have this very interesting and important inequality that a variational C segment always satisfies this type of one convexity property of the distance square. Okay. In fact, when you're on a PC space, so positively curved space, geodesics satisfy exactly the reverse inequality. Okay. And sometimes you need not the reverse inequality, but inequality in this direction. And this is exactly what led Ambrosio, Gigli, and Savare to construct generalized geodesics when looking at gradient flow in the Wasserstein space, which is a PC space. Okay, and so this is a way to maybe say to identify a subclass of segment that satisfy this property. Okay, variational C segments do satisfy this property. Okay. And maybe I will pass. How much time do I have left? Huh? 0? Okay. So I will just end on this example. That maybe the most interesting example is that if you have a base cost that is an NCC, then the transport cost based on that cost is an NCC on probability measures. And in fact, it's an equivalence. Okay. So in particular, the square Vasarstein time distance on Rn or on the sphere are NNCC spaces. And so you can construct always versional C segments. And essentially, versional C segments are generalized geodesics or the equivalent, the analog or the extension with more general cost function. And then also, I want to mention that the Gromov-Wasserstein space, which is known to be positively curved metric space, is in fact something a bit stronger. It's an NNCC space. Okay. I think that was it. Thank you.
Thank you, Flavien. Questions?
Can you state more precisely what you say about convergence of the Newton scheme without any assumption on the initial state?
So I said that, so I showed you an explicit scheme. Newton is a form of this explicit scheme when U is equal to F, as Robert said. I showed you a theorem that says if your function is convex along versional C segments, then you will have convergence rates. So I just need to say what are those versional C segments. If you write them a little bit, you will obtain that. So if I remember correctly the formula. So if your function satisfies this property, then you get rates of convergence. So it means that for Newton's method, it's not convexity on normal segments, but it's convexity on different kinds of segments, these versional C segments. Once you write down everything, you will get a condition in order to get rates. So this is the kind of convexity condition that depends on 3 derivatives of the function. So this is 3 derivatives, so you get 3 slots, right? And so here, this could be a test function. And this part corresponds to the C concavity that you need in order to have rates of convergence. Is that? And it's strictly different. There's an overlap, but it's not self-concordance. It's not. So self-concordance is a condition that is often studied for Newton's method that also involves 3 derivatives of the cost function, like this one, but they are different. Yes, yes. I don't have it in mind. It's something with logs or exponential.
And what you get in this case, it's an exponential convergence.
So here I wrote it without the mu parameter. I think with the mu it's probably something like this.
So otherwise you get,
and then you get
a slower convergence than what we use.
But actually, it turned out that even with 0, because Newton is so special, you always get exponential convergence.
Okay.
Yeah, even like no matter how far you are, if you satisfy this condition. If you think this condition is too crazy, it means that Newton is not meant to globally converge. Okay, so but this explains why. Then you need to satisfy this condition. Yeah, and so this is all about C concavity, right? This is just cost function that everything is very geometric, so it's definitely affine invariant in particular, because the cost itself is affine invariant. Okay, it's late, so let's just.
Other questions? Otherwise, we thank Flavien and all the speakers of today.
Thank you.